All right. Good morning, everyone. Welcome to Denmark. Welcome to Copenhagen. Welcome to ISMM this year. My name is Jay Lee. I'm a professor of computer science in Seoul National University. So let's start. Okay. I can actually start this session with perhaps the most important information of the day, which is about the meal schedule. So the lunch will be offered in the Fellini restaurant, which is on this place on the first floor of this hotel. If you had breakfast, that's the place where you actually had the breakfast. So please make sure you had your lunch, starting at 12:20. And then welcome reception dinner is also scheduled today, starting like at 6 p.m. today. So please come join us. By the way, this part of the introduction is supposed to be given by the Michael Bond, who is the general chair of the conference, but he actually has a little bit of trouble in traveling, so I'm going to present this part. I want to give a big thank you to all of these ISMM steering committee members and PLDI organizers who made this happen. By the way, if there's anyone, I see Steve here, and then anyone else who in the steering committee, please raise your hand. Also PLDI organizers like Jishan, I see Jishan, and please raise your hands. So let's give them a big applause for thanking their services to make this happen, all these events. And also I want to thank the chairs and the PC members. As I said, Mike Bond, he was the general chair of the conference, and then program co-chairs myself and Hannes Peyer from Google. And we also have very stellar group of PC members from with various different expertise. So I would really thank all these PC members for their hard work to selecting the best work submitted this year. Proceedings. Probably you may wonder how you can access the conference proceedings, and the proceeding itself is already uploaded in ACM digital library, so you can directly access from there. You can just do Google search ISMM 2024, then probably you should be able to find it. Or there are two options. You can also access these proceedings. So option one is if you go to the program page, there is these DOI links on each item, each a paper. So you can actually click it. That actually directly goes to the ACM digital library entry for particular paper. And also if you prefer, go to the top page of the proceeding. We also put this ISMM 24 proceedings link on our a landing page. So just go to the ISMM 2024 conference webpage. Then you should be able to find either the links to the top level proceedings or the links to the individual papers. Okay, from here I think I will. Take over.
Thank you. Also, welcome from my side. Thank you again to everybody who contributed to ISMM, to all the attendees. Without you, ISMM wouldn't happen. For the call for papers, we basically started this already a couple of years back. We continued expanding the scope of ISMM and encouraged more submissions from other fields that are very related, in particular computer architecture and operating systems. We made sure that the submission deadline was not just only aligned with the notification of PLDI, but also ASPLOS and ISTA this year. You can read the call for papers in detail. You'll find it on our webpage if you haven't done that already, which is quite diverse at this point and pretty broad. In the call for papers, we asked for regular paper submissions, but what started last year, we continued also this year. We asked for intellectual abstracts, practitioner reports, and surveys. And we had 17 program committee members, and somehow by accident got 17 submissions, which was great. So we ended up giving every reviewer 4 papers to reviewers. Out of these 17 submissions, we had 12 full papers, 3 intellectual abstracts, and 2 practitioner reports. We used the standard SIGBA and double-blind reviewing process. As said, each paper got 4 reviews. Authors had the opportunity to engage in a rebuttal, and then there was no program committee meeting. We did that fully asynchronously and wanted for each paper basically an anonymous decision for accept or reject. In the end, 8 full papers and 3 intellectual abstracts made it to the program. The program will look like that. We will kick it off. Oh, we lost the screen. And now we're back. The program will look like that. Like we kick it off with a keynote of Andreas Rosberg talking about WASM's evolution model of store. And then we have a coffee break followed by 2 sessions. There will be lunch break. And then we have the second keynote by Dr. Oitio Lim, enabling the AI revolution, next generation memory solutions for AI computing systems, followed by another session, a shorter coffee break then, like it's a bit shorter than the traditional one, the original planned one, but we had a bit, our session was a bit too long to squeeze in. Then we end with another regular paper session in the end. Brief announcement in the end. ISMM next year will be again co-located with PLDI. It's going to be in Seoul, Korea. And we already have a general chair, Martin Mas from Google, accepted this position a couple of weeks back. Cool. And now let's move over to the program. It's my great honor to introduce our first keynote speaker, Andreas Rosberg. Andreas received his PhD from Saarland University, was at Max Planck as a postdoc after that, then moved to industry at Google, where he was one of the designers of the WebAssembly language. He moved to Dfinity afterwards and is now an independent researcher, still deeply involved in the WebAssembly specification process and is champion of various proposals there. His research interests are pretty broad in the field of programming languages. But to quote him, ranging from foundational theory over design to implementation, as long as they are not ugly. So please, Andreas, come up. We're looking forward to hear your keynote.
Is this on now? Yeah. Okay. Yeah, thanks for the nice introduction. So another talk about WebAssembly. At this point, I almost feel like a one-trick pony, to be honest. But so when Jay and Hannes invited me to give a talk here, they asked me about talking about WASM GC, but I had to point out that I just gave a keynote about that at MPLR like half a year ago. So I decided to basically broaden the topic much more to what's the story with memory and WebAssembly in general, right? And I will talk about GC a little bit, but won't have time to go into depth because there are so many other things to cover. So it will be a bit like here and there, but I hope it's still interesting. So yeah, WebAssembly. Oops. Yeah. Come on. No? Yes. Or WASM, as we usually call it. I guess you've all heard about it at this point, right? But I want to give you the one slogan that really describes how you should think about it. It's a virtual machine, and particularly it's a low-level virtual machine. So virtual machine in the same sense that a JVM or something like that is a virtual machine, but very different in the sense that it's low-level. And that's a key design point of WASM. So what do we mean by that? This isn't really. So looking back at WASM 1.0, the very first version of WASM that we released in 2018 or something, basically what it means there with respect to this talk is two main things. One is that we really only have very primitive data types to compute with, right? Basically machine types, so raw number types. That's all you got as values of computation. So concretely, this doesn't really, there were only these 4 types originally, right? That's all you had, like floats and integers. And the other way in which it is very low level is that the main memory is really just a flat array of raw bytes. That's where you have to store all your data, and you have to manage it by yourself entirely, right? Probably should so, and it's so primitive there isn't even a notion of pointers, right? All you have is integers, and you use those to index into that flat memory. Use that as your notion of pointers. So to give you an example, if you've never seen WebAssembly before, this is like in the text format anyway, you can define a memory like this. And what that says is, okay, define me a memory with 5 pages. Initialize it with zeros, and a page is defined to be a 64K block of memory. So you have to give like an initial size, and it can be anything from 0 to something much larger. And then you have instructions for operating on this memory, like the load instructions you would expect from a CPU, for example. And we can describe these instructions with what we call instruction types, which look like this in WebAssembly. So this is telling you this instruction pops an I32 from the operand stack, so WebAssembly is a stack machine, and pushes back this is not good. Pushes back a float, right? So this is loading a float, and the operand is just an offset into the memory, and that's where you load these 8 bytes from and return them as a float. So yeah, this is what we call an instruction type, and that's a good way to understand some of the instructions. There are various other instructions like that, so you can also load smaller portions. So as you saw on the previous slide, I32 is the smallest integer type we have. So if you load something smaller, it's going to get extended, and you can pick which way it's going to get extended to I32. And similarly, you have store instructions. So here you see the instruction type saying that this actually pops 2 values and doesn't push anything. So epsilon is the empty list of things, and every instruction can, in general, push and pop an arbitrary number of things. And yeah, and there's a whole family of these. Basically, all combinations you can think of are available, right? So no surprise there. That's how it's really low level. That's all you got to access the memory. And then there are a couple of things to note here. First of all, access to the memory can be totally unaligned. That's fine, and it's well defined. It may be slow in some architectures, because it has to fall back to some slow path if you have unaligned access, but it's always well defined. And the other thing is that in contrast to that, out of bounds access, like when you try to access the memory beyond its size, is not allowed and will reliably trap. So trap is our notion of basically aborting the program. So this is, every access is checked. This is usually implemented in an engine using virtual memory techniques, so doesn't have any overhead, although on some implementations it can. But yeah, so that is what makes WebAssembly safe, memory safe, right? So this is really relevant. And then there's one more thing. So the memory there is declared with a certain size, but you can actually grow it dynamically. So there's one instruction that takes a delta in the number of pages by which you want to grow the memory, and it returns the previous size. And this is because WebAssembly is really a pure computation engine, right? It doesn't have any operating system whatsoever, so there's no other way than adding an instruction to allow allocating something from the environment, essentially. So this extends, if you want, the address space with additional pages. Right. So this is a very simple model, which is nice, right? It's easy to implement, and it's easy to implement efficiently, but it has another upside, which is really that this is what provides language neutrality, right? By being low level, by being an abstraction of the hardware and not of any specific language constructs above you, we are really achieving language neutrality in a way that would otherwise not be possible. So as far as I'm concerned, that is the only way to actually be language neutral, because with any sort of more high-level mechanism, you inevitably start being biased towards certain languages, certain notions of programming language. And that also means that when you compile a high-level language to WASM, of course, you have to basically do the same thing that you have to do when you compile to native code, right? And that's fully intentional. So, and that's also, I mean, you have to do more work in some cases, but it also means that an existing compiler to native hardware, you should be able to just write a WebAssembly backend for that without having to redo the entire compiler pipeline. So in a way, that's also a feature.
Just one thing. Would you mind reduce the resolution of your laptop a little bit? Maybe it should help.
The resolution.
Maybe full HD or some reduced resolution.
Okay, let me try that. Where do I even... I'm not sure where I do that, actually. Yeah, but... How...
I think this HDMI to USB and
okay.
ASC. Oh, this is default. Maybe it's even lower one. Like, what about
This one?
yeah, maybe you can try that one.
Let's try again. Oh, this might be empty slide. Okay. Yeah, let's see. Thanks. Hopefully that works better. Not really.
Sorry, maybe it's better to go back.
You could also try turning off the true tone display.
I already did that. Yeah.
Let's try how it works.
Yeah, let's, okay. Okay, where was I? Oh, sorry, that was too fast. So, yeah, basically you should think about WebAssembly. Another way to think about it, instead of a virtual machine, it's really a virtual instruction set architecture, right? So very close to CPUs. And the idea is that every WebAssembly instruction has a one-to-one mapping to actual hardware instructions. In the first approximation, there are some couple of exceptions, of course, but right. So, so that is the basic kind of picture that many people have of WebAssembly. You've seen it and how it's often represented. But it's actually a bit an oversimplification and a misrepresentation of what's going on with WebAssembly. And I've seen that representation in papers even. So I want to point out a couple of things in which it is actually a bit more than just that. So there are some myths, I call them here, that I have seen in various places. So the first myth is that this is the only memory you have. That's not true, right? Because WebAssembly has at least two other things, other parts of global state, which are global variables. They are what you would expect, and tables. So I don't think I have to explain what globals are, but tables, if you don't know WebAssembly, might look a bit weirder. So let me briefly explain why we have them and what they are. Basically, they were a way for the original version of WebAssembly to be able to map C to WebAssembly, in particular the notion of function pointer in C. So this is how they work. So imagine you want to compile a program that has a bunch of functions in it, doesn't matter what they are, and you want to be able to form pointers to these functions to be able to compile C, right? Or represent something similar to C. So the way you do that in WebAssembly is you define a table, let's say of 5 entries to hold the 5, to correspond to the 5 functions, and you have to declare that's a table of function references. And in WASM 1.0, that's actually the only type a table can have, so it's kind of was a forward-looking syntax if you want. And then you can initialize this table with the functions that we have defined before. So this is saying at offset 0, put in these entries into the table, and that initializes them at startup of the module this is defined in. And then we can have code, for example, some function caller that wants to call through a function pointer. And this function pointer we can now represent as an I32 simply, and that's just an index into this table. So we have this indirection through the table to access rules as the assumption that tables are mutable. That's not actually true. In WASM 1.0, there are no instructions for mutating tables, but you can mutate them from the outside. So if you export a table to the host environment, for example, on a web page that might be JavaScript, then JavaScript has an API for mutating table. And that can happen anytime under your feed whenever you do an external call. So here would be an example of a module that imports some function and defines a table that it exports. And then initializes it with, and for the sake of this example, the table has just one entry, but it initializes it with a stupid function that just returns a constant. And then I have another function which performs a call through that table. And you would assume that this can only like return 42, right? But that's not true because we are performing a call to I beforehand. And this call to I may mutate the table in any way it wants. So we cannot assume that the table is still in the same state after that. Here would be some piece of concrete JavaScript code that would expose that. So we compile this module, we extract the table from the exports, and then as the import for the function I, we pass a function that just mutates the table, right? So you cannot assume that tables are mutable. And finally, another thing that is often misunderstood, that's probably the most subtle one in a way, is that there is only one memory. Yeah?
Was that something like a strong update because it mutated a
Was that something like a strong update that changed the type of the object in the table because it mutated a WASM function, replacing it with a JavaScript function?
Good question. I'm going to get back to that. So tables are actually not typed, at least in WASM 1.0. It's just saying funcref, so that's a dynamic type of all functions. And call indirect actually has to perform a type check at runtime. So at the call side, you know what you expect, but that requires a check actually. Right. So it's not true that there's only one memory in a program. The actual restriction is there's one memory at most per module. But a program can consist of multiple modules and you can link them together, right? So here's an example of a module that defines a memory and exports a load function for that memory. And then I have another function, another module, which also defines a memory and imports that load function from the other module, and then has some other piece of code that first stores some value into its memory and then calls the load function from the other module. And this will see a completely different address space, right? These two memories are completely disjoint address spaces, so you will get back 0 here and not 42. And this is important to understand. So really, an application can have an arbitrary number of memories if it wants to. They just can't be visible in a single module at the same time, which is sort of a silly restriction, but there were reasons for that. But I'm going to get back to that. Right, so they're really separate address spaces, and if you want to share them and make them one, then you have to do that explicitly by importing and exporting in the right way. Right, I already said that. Okay, and same story with tables. Okay, so to sum up the story of what we had as store as memory in WASM 1.0, there are like these three things: memories, tables, and globals. They can all be mutable. Globals, you can have many per module, the other two only one per module. And memories can only hold bytes, so numbers, whereas tables hold function references. And globals can hold values, and in WASM 1.0, that is really the same as numbers. So this is a nice and simple model, but perhaps it's a bit too simple, right? Because it has various serious limitations. So let me go through those. So, I mean, this basic idea of using or abusing, if you want, integers as pointers is nice for like internal pointers in your program, in your module, in your runtime that you construct. It's not a great thing if you need to handle external pointers, so pointers that the host environment gives you, like on the web, pointers to some JavaScript object, right? What do you do with these? You can't expose their representation. That would be completely unsafe, right? In the same way, exposing function addresses would be completely unsafe. So there isn't really a good way to handle this. And you cannot allow them to be stored in the WASM memory as well, because that would expose them. So what some applications do when they actually need to manage external references like DOM objects in WebAssembly code, they have to construct and maintain this bijective mapping at the boundary between like external pointers or objects and integers. And this is, as you can imagine, as brittle as it sounds. It's basically manual lifetime management of the cross-heap pointers, and with all the problems that has. I mean, this audience, I don't have to explain that this is terrible, right? Okay, so, and I mean, function tables have a similar problem. So we have function tables, and the idea is that they basically abstract away function pointers, function addresses. But that also creates the limitation that, okay, now I can only statically initialize it, and that might be quite limiting. There's no way to dynamically like initialize or mutate a table from within WebAssembly, which you often might want. So one particular pattern where you want that is if you want to implement dynamic linking, right? Then you actually want to add entries to a function table later, things like that. So, and the other thing is, coming back to your question, because we don't really know the type of the things in the function table, we have to perform all these type checks because our type system can't track what's in the table, and it can be heterogeneous. And that was actually very intentional, because to compile something like an OO language like C++, you need to represent vtables in memory, and those are like totally heterogeneous, right? And it would be pretty messy if you had to distribute that over multiple tables. Okay, and these are reoccurring issues. So there are various proposals in the pipeline for WebAssembly, like exceptions and continuations and garbage collection, which I'm going to talk about later, which all run into the same issue. You have some notion of pointer in the underlying implementation, like the engine, but you cannot expose that to the user space because that would be unsafe, right? So how do you handle these? And with WASM 2.0, which arrived like 2-3 years ago, like one of the main additions there was hence this new notion of references. So references are now a new form of value, which are really first-class pointers. And for WASM 2.0, there are only two reference types, which are function references and external references, like the two ones I talked about. But of course, with the idea that we can extend that later to many more. And importantly, these are opaque values. You can never like observe their concrete representation, which also implies that you cannot store them in memory. Okay? That would again be unsafe. And you cannot convert them to numbers either. So this is really essential for security and safety. But okay, so you have these things, but how do you store them then if you can't put them into memory, right? And there the second idea was that we're going to repurpose the notion of table we already have and generalize it. So instead of just allowing functions to be stored there, we can now store arbitrary references. And also because we now have multiple different table types, we also have to allow multiple tables that correspond to different types. So. And we add instructions now to actually manipulate tables from within WebAssembly. And in the same way you have memory grow, you have something like table grow now because you actually need to have the same amount of generality. So the general picture now is that WebAssembly values are separated into two categories. We have numbers and we have references, and they're really disjoint, right? And numbers are these like primitive number types. There's another new one in 2.0, which is the vector type, which I'm not going to talk about here. You can think of it as another number type if you want. And for references, for now, we just have these two. And the main characteristics is our numbers are like these transparent values. You can observe every bit in them, and thereby they are storable in memories, and like kind of dually, you have references as opaque values, and you can store them in tables. And value and globals can hold either of those. And yeah, so basically this means we have created the symmetry where tables are to references what memory was to numbers. Okay? So going back to like the summary of WASM 1.0, what has changed now in WASM 2.0 is that we can now have many tables and they can hold arbitrary references, and values can also be references. So this was a relatively minor update to the language, but I mean, this is somewhat fundamental. And this is still, this is still arguably fairly simple and nicely symmetric, having these two kinds of storage, right? But really, we're just getting started. So there's still some limitations here. First of all, we still only allow one memory per module being accessible. And there are actually many use cases for multiple memories, as it turns out. So without going into too much detail, you want to like be able to encapsulate memory. So like a module might want to have a private memory for itself and a public memory to share with others for safety, security reasons. You want to do virtualization or instrumentation where you have a side memory to put in stuff without changing the actual code, things like this. But it's pretty annoying that you can't do that in an efficient way, right? In particular, like any access to a secondary memory now requires a cross-module call because that's the only way to access another memory, right? And moreover, there's absolutely no efficient way to copy between memories. You really have to do that word by word using cross-module calls, which is just silly. And another important problem here is that this also makes WebAssembly non-compositional, so on the module level. The module system is an important part of WebAssembly, and it has this nice property that you can manipulate them in various ways. And one way is when you have two modules that somewhat import and export to each other, you can statically merge them into one module by just like unioning all the definitions, except when both of them have a memory. So in WASM 2.0 that did not work. That was the exceptional case that did not work, and that is really annoying for some tool chains and for the generality of the language. So obviously we want to get over that. But that was the simple part, and then there are all these like high demand features that people really want from WebAssembly, and that's going to be the major part of my remaining talk here. So things like larger address space, things like page sizes that can be customized because you're running on very limited hardware. For example, like embedded systems. There are lots of users of embedded systems now that run WebAssembly. And for them, 64K is quite a lot of memory. So they want finer granularity. And then, of course, garbage collection. I already mentioned that a number of times. And the other big thing is threading, right? So far, WebAssembly is totally single-threaded. But of course, people want threads, understandably. So in the upcoming next version of WebAssembly, which I just christened 3.0 here as like, I know this is not official version number yet, but think about it that way. That will support all of that, right? So it's a major update to the language with quite some complexity. And this is what I'm going to talk about for the rest of my talk. So let's start with a simple thing. So multiple memories is really just essentially dropping the restriction that there can only be one memory in scope. And on top of that, we now have to extend the instruction structure so that they all take a memory index to know what memory you're referring to. So like they have now this immediate there. There is, of course, a cost involved with that, and that was the prime reason why we did not do that initially, right? So usually WebAssembly engines, they pin a register using it as the base address to the memory, the one memory that every single piece of code can see. But if you have more than one, that doesn't quite scale anymore, so you either have to use indirections or multiple registers. I mean, there are various ways to implement that, but in general, there might be a cost involved with that, especially for the non-primary memories. And one important thing to note here, because that confusion often comes up, even under this extension, memory indices are still like completely static, right? They are hard-coded into your instructions. So that means that you really have a strict partitioning of address space. You have to statically know what memory any address refers to, really. And if you wanted to actually have like memory pointers, some representation of that, like sort of segmented pointers if you want, that consists of a memory index and an offset into that memory, then you would have to switch on the index and have separate code paths for the loads for every single memory, right, or stores. So this is not really designed for doing that, but people sometimes misunderstand that, right? And there would be designs that would support that better. In particular, essentially, what we would have to do is introduce memory references as first-class values too, that you can then store in a table, for example, and then you have, similar to call indirect, you have load instructions that take a dynamic memory reference. But that's not what this extension is. This is much more much simpler, and so far there hasn't been like heavy enough demand for that to actually be turned into a proposal. Anyway, so that was just a clarification. Then 64-bit address space, that was often requested, right? Because WebAssembly so far only allowed 32-bit offsets into memories. And the way we do that, so here's some code for WebAssembly 1.0, which is just the implementation of a string length function over that memory there. And with WASM 3, you can turn that into 64-bit code simply by changing the declaration of the memory. So we introduced this notion of an index type now, which you can declare with your memory, and that determines what the type is with which you index into that memory. So the type of instructions over this memory are now determined by this declaration. And of course, that means that we have to fix up the types here, otherwise this code wouldn't be well typed, but that is really all you have to do, and now you are 64-bit address space. Somewhat similarly, custom page sizes. So here's some very stupid allocation code. So far, if you really want to do allocation by directly using memory grow, then you have to essentially round up by pages. I mean, this is stupid code. You wouldn't do it quite like that, but just to, as an example. Well, what you can do now is you can declare the page size of a memory. And in this case, I say page size 1, so I can now grow it with a granularity of single bytes even, right? And for embedded systems, that is what they want. So that means that what that implies is that memory grow and memory size, these two instructions which operate in terms of page sizes, are now like operating in terms of that declared page size. And I can simplify the function there, and it's going to be more precise. And for now, we have decided to really only allow page size 1 and 64K. But we may add others in the future if there's a need for that. So far, we didn't feel like there's strong evidence that any other page size in between is beneficial. Okay, and one thing I want to point out here is that both these extensions really made use of the fact that WebAssembly is typed, right? That we have types even for things like memories and tables. So because what we did is we just generalized the notion of the type of a memory here. So that now has these various components. So it defines an index type for the memory. It defines a minimum size that you saw. It also defines optionally a maximum size. I didn't show that so far. And now you can also define a page size for a memory. And similarly with table types, they're generalized in the same way. So they also have an index type now. And this is very nice that we were just able to add these features without even extending the instruction set at all, right? It's all driven by the types, by the type system. So the point I want to make here as a person who's into type systems, types are nice. Types are useful, and they can be quite a simplifying factor. So types are really your friend. You should always think good of types. They can simplify language design quite severely. Okay, so those were the simple ones, and the two big features in WASM 3.0 are garbage collection and threads. So let me talk about these. Garbage collection is an often requested feature and has been in the making for I don't know how long, since probably 2018 or something. Of course, first question everybody asks and should be asking is why do we need to build in GC, right? We have the memory, we can do everything we want. Well, that's true. You can roll your own garbage collector in the memory, and runtimes do that, and it's totally a viable approach, and some languages will definitely continue to do that for various reasons because they need to have more control over what's going on. But it comes at a cost. There are some drawbacks to that. So one is that this is sort of like implementing a GC is sort of kind of the worst case scenario in terms of the abstraction barriers you run into with WebAssembly that are there for safety reasons. Like you have no access to the stack whatsoever, so you can't like find roots on the stack yourself. You have no access to registers, all of that, right? So what you have to do in practice is you have to maintain a shadow stack where you spill all your roots, and that is extra cost and complexity. And it also doesn't solve the problem of exchanging references with the host environment in a safe manner, right? Like the same reason we introduced externref also kind of applies in the inverse direction. And of course, if every language does that, or every piece of program ships its own GC, and you have a web page with multiple, I don't know, plugins, whatever that get loaded, you run into this problem of having multiple language runtimes that compete with competing heaps, that compete with each other for space. And with the host too, because the host, of course, is also a managed language usually, right? So again, you have this multiple heap problem and all the performance implications that come with that. That is very annoying. And of course, another more like pragmatic thing is also that good GCs are not simple programs at all, right? So the one number I remember, there's support of Mono to WebAssembly, and I don't know, many years ago they gave a presentation and said that the GC alone is something like a megabyte of WebAssembly code. So as part of the runtime they have to ship, right? And if you have to do that for every single page or every single plugin on a page, that's kind of silly, right? So in particular, since at least on the web, the engines already have like these super highly optimized industrial strength GCs built into them, probably the most optimized ones you can find. So it would be sad if we couldn't like reuse them. So that's what this provides. But at the same time, we want to stay true to the idea of WebAssembly being a low-level language. And obviously, there's kind of like a conflict there, right? Like, what does that mean? We're adding something more high-level now. And the slogan I've been using for some time now is about what WebAssembly is supposed to be is like really as low-level as you can go, right? But there are some limits to that, of course, which some abstraction boundaries or abstractions you have to introduce for safety or performance reasons. So as low as possible, but no lower. But that also means there are some very explicit non-goals with the GC extension. So first of all, like the direct consequence of that, no high-level constructs, right? In particular, God beware, no object system. Like we don't want to build anything like that into WebAssembly. Also, it doesn't give you any like magic, seamless multi-language interoperability. So this is also a thing that people are often confused about when they hear about the GC proposal. They now expect that, now all these languages can talk to each other easily. No, not at all. That's not what this gives you. And that was actually never a goal for WebAssembly in the first place, right? Language interop, or seamless language interop was never a goal for WASM at large. And the reason is that I mean, there's simply way too much diversity across languages. If you have seen N language implementations, you know that this is never going to fly, really. There are so many impedance mismatches, even between closely related languages, that in reality this never works. Unless you turn one language into the other. And the observation is here, like if you want this interop, well, what do you do in native space, of course, is you define ABIs, right? And you can do the exact same thing with WebAssembly. There's nothing preventing multiple compilers from agreeing on some ABI, but that is completely separable from the actual WebAssembly specification. That could be a completely separate standard on top of WebAssembly. Yeah, and from my perspective, this is really key to WASM's success as a language-neutral abstraction, that we do not try to solve these problems. Okay, so what do we do then? Like, what is it that we add as GC? Like, really the bare basics? Well, we only give you a way to describe memory layout, like things you want to allocate. And that's what the types describe. And so these are not at all like source level types. They don't have the same complexity. So they should really be easy to produce by a compiler, but also to consume by an engine. And what that means, of course, is that if you have a high-level language with some Rube Goldberg type system, then you have to lower this type system into WebAssembly types. The same way you have to lower code, right? You have to lower types. So you have to map these types into representations in the runtime. And basically, you're describing to the GC the layout of the data structures, the same data structures you would use in a native compiler or if you compile to the linear memory, right? But you declare them to the GC so that it knows how to handle them. But that's all you do. And all this is also supposed to be pay as you go. So if you don't allocate anything, then you shouldn't pay any overhead at all. Right, so what this ends up being then is really the GC extension just adds 3 basic things that you can allocate. It's tuples, arrays, and actually scalars. So tuples and arrays are what you think, or tuples or structs if you prefer, right? And scalars are a way to also expose the idea of having tag pointers like unboxed integers. So being low level, this is pretty important. Like all serious production engines for high-level languages use some form of pointer tagging, or most of them anyway. And so you want to be able to do that as well when you compile to WebAssembly. And one thing I keep forgetting to point out, and people then ask me, is like the GC heap is like completely separate again from any memory or any other kind of store in the WebAssembly engine, right? So it's not mapped into the heap because that into a memory, because again that wouldn't be safe. Okay, so more concretely, we now have new forms of type definitions in WebAssembly, so you can define structs or arrays, and we have new forms of reference types, which are reference to a particular type, right? So where we before just had funcref and anyref, you now have like fully typeful references that concretely say what you're pointing to. And you can also have these for function types now, by the way, which I won't really talk about here, but you also have type function pointers as a side effect of this. And the other thing you have, which are these scalars, is like this special thing called a reference to an I-31. So, and it's called that because, well, we have to reserve one tagging bit. So the the largest value space we can guarantee to be unboxed on any architecture we care about is like I-31, 31 bits. And then you just have like sort of the canonical set of instructions you would expect. There's nothing really interesting going on here. So you can allocate these things and you can access them. And for arrays, you can also inquire the length. And there are a bunch more for convenience, but really those are the core primitives, and that's all there is to it, right? Everything you do now is like declaring these types, which define your memory layout of your data structures, and let the GC take care of deallocating them. So yeah, typing here is important because the references now are like, as I said, they are now concretely typed, and this gives you strong typing, and that is important not just for safety, but also for performance, right? So this really says, I have a reference to a non-null reference here to a point data structure, and that means that I can compile this access to that data structure without any check whatsoever. It's directly compiled to a load instruction in hardware, right? Because it can never fail. We know that from the type system. And these types are also like transitive, you know, transitively what things are pointing to. So when I have a reference to points, which is an array of points, then when I get an element of that array, I also know its type, right? So like you would expect from a fully typed programming language. You have subtyping too. I'm not going to talk about that, but it's also important for avoiding unnecessary overhead. However, of course, like there are super powerful type systems out there, right? And you can't expect that you can map every type system in the universe to WebAssembly in a type preserving manner. That will never work, right? So you can never have a type system that subsumes everything out there. So there absolutely has to be some escape hatch, and the usual escape hatch is you have some form of cast, right? So these are casts that take a reference of some type and you check that this is actually having a specific subtype you expect. And the types, again, being just the shapes of the data, right? So this checks kind of like a type descriptor in the object, in the heap object. And there are a bunch of instructions for that, like more or less what you would expect. Right. So how much time do I have left on this? 20 minutes, okay. So I try to briefly run through at least part of an example I had before, which is how would you use that now? And the classic example is how do we compile classes, right? So let's take some pseudocode object-oriented language. I have a class that defines one instance variable and two methods. And let's say I also have a subclass of that extends it with another instance field and another method. So the way you would compile it usually on native hardware is, well, you represent instances as these objects which have all the fields there, and the first one is a reference to the method table. Like in the C++ universe, they call that the V table, right? And the V table, again, is just some tuple of function pointers, essentially. And similarly for D, like the subclass, the instance types are like the extension of that, the one for the superclass. And what is important here for this to be correct is actually that these are semantically in a subtype relation, right? And similarly with the class tables. So when we map that to WebAssembly, we actually have to somehow achieve this subtyping for real. So let's see how that works. So this one we can lower to a bunch of type definitions now. So the instances of C, they are just structs where the first field is a reference to the corresponding V table, like just following essentially the diagram, right? And then there's the I-64 field for representing A. And the V table itself is again just a struct which has the reference to the functions. And here you can see that we also have type function references now. And all of these are non-null, right? You can actually distinguish in WebAssembly whether a reference can be null or not. I did not show that anywhere on the slide, but if you say ref null something, then it's a nullable reference. And here we don't need that. And the function types for the two methods are what you would expect in an typical implementation of an OO language. So they have the parameters declared there, but they always get this implicit first parameter, which is the self, this or the receiver of the method call. Okay, and then the subclass, we do the same thing. Now this is extending that type with the additional field for B. And similarly, the V table here is extending that one with the additional field for the H function, which has the corresponding type. And it turns out that when we do this, these are actually in the subtype relation we need in the WebAssembly type system. We can declare them that way, and that will work out. So that means that even on the level of WebAssembly, you can pass a reference to D wherever a reference to C is expected, so you don't need any casting. Now, there are cases where you need casting. I threw out the slides for that because I thought I don't have time to really go through that. But the point is when you override a method, then you get into this usual like covariant parameter issue, right, with the receiver. So that means when you compile a method that is an override, then the first thing it has to do is a downcast on the receiver parameter to its own type. But that is the only place where you need that when you compile like a simplified object-oriented language. Okay, so that is the whole idea. Really, you basically do what you're already used to, but you have to make it a bit more explicit by declaring these types. Yeah, and this is how a piece of code would look. So this would be the implementation of the method f now, which is really just accessing the receiver like this and then adding to it. And a call to that method through D, again, is compiled in the way you would expect. You call through a reference, so this is also a new instruction now, which is a call through a function reference, which is fully typed, so does not require any type check, unlike call indirect. And the function you call is the one you get from by accessing first, like the first field of D, which gives you the V table, and then accessing the first field from the V table, which is the function f. And then you call that with the additional parameters, like the actual parameter and the self type. This is what you do in native code, so it should not surprise anybody. Okay, that's all I'm going to talk about GC here, because there's another big thing, which is threading. And that has also been in the making for a long time, It was almost shipping, or it was actually even already shipping in some browsers by the end of 2018, and then Spectre happened. And it was unshipped like in panic everywhere because we were now exposing concurrent, like high-performance concurrent storage and all. Like, there was a high fear that this could result in the ability to do timing attacks on WebAssembly through Spectre-like approaches. But now, like, and the other reason why it took so long was that, yeah, we'll get back to that, memory models, right? So, but let me first clarify what we actually mean here by adding threading to WebAssembly. It does not mean what you expect it means. So, unfortunately, it does not mean that we have the ability to actually create a thread. And this is really annoying, but this is something that was imposed on WebAssembly from the, like, web platform folks who really don't want this to happen in the web platform because web platform is single-threaded, and they basically want to keep control over that. And there would be ways to completely encapsulate that, but still, like, it was a highly political topic. So instead of being able to create threads, you merely have the ability to observe that there are threads, and they are created on the outside. Like in the web, on the web, it would be a web worker, for example. In other environments, there could be other means. And of course, the actual functionality we're adding are now like instructions for synchronizing between threads, so atomic memory accesses. So, and basically the ones you would expect: atomic loads, stores, exchanges, and a fence instruction. Right, so again, we're utilizing types now. So what you have to do to use atomics or shared memories, you actually have to declare it. So a memory can only be shared between threads when it is declared to be shareable. And that has various advantages, in particular that, like, when you have a non-shared memory, you can access it more efficiently in many places. I will actually explain a number of other advantages. Let me first go through the example. So yeah, so this declares that the memory can be shared. And then I can implement something. I won't really walk through the code here, but this is an implementation of a mutex lock, and you can see, like, occurrence of atomic instructions in there, and they kind of do what you expect. Like, the first one is an exchange instruction. We have atomic store there. And then we have this other thing, which is a wait and notify queue. This is, again, a thing that's usually provided by operating systems, not really by hardware. But since we don't have access to an operating system, we have to turn it into instructions. Okay, so really, everything should be what you expect from atomic instructions. But the big thing now is, we now have threads, we have shared memory, and we get into all the nastiness of memory models. In particular, we want to, of course, expose the hardware instructions without any additional cost, ideally, right? Or at least minimal cost, which means now we expose all the craziness of memory models in hardware. Relaxed memory models. If you ever had the pleasure to look at, at that stuff, it's disgusting. Right? And at the same time, we want to preserve WebAssembly's property of having a well-defined semantics, right? So one thing I didn't mention yet, and the thing that I'm particularly proud of, is WebAssembly is a fully specified, formally specified language, end-to-end, right? Every single bit that can happen is specified. There is no undefined behavior whatsoever. And relaxed memory models are usually not at all like that. They're quite brutal in allowing undefined behavior all over the place. So we have to deal with that. And that, again, because we have to be safe and we want to be portable, right? And roughly what we do here is we adopt something that is close to the C++ model, but with fewer features and, more importantly, a sanitized version. And for now, we also only provide sequential consistency for atomics, but that was just a decision for keeping it simple for now, and we can always extend that later. So I don't want to bore you with all the details of the memory model, but just want to point out a number of challenges we had for WebAssembly here that you don't usually have when you do something like this for C or some higher level language. So the one is, of course, the one I already mentioned is that we have to avoid undefined behavior. Like, not an option at all, right? So even when you have data races or out-of-bounds access, all of that has to be well-defined. It could be non-deterministic, so under-specified. There could be multiple different outcomes, but it still has to be defined. It has to be a set of possible behaviors. And the way we do that is essentially, like non-atomic accesses essentially are roughly similar to the semantics for relaxed atomics in C++. So it's not really non-atomic, it's kind of more like relaxed atomics, including the ability to get out of thin air values, unfortunately. The other difficulty is we have bounds checks, right? So you have to model that as well, and they are kind of atomic with the actual memory access. And the way that is modeled is that we assume that every memory has a virtual location, which is its length, and you're reading that length atomically with the actual value. And then these reads to the length location can also be ordered in the way you would expect. But it's more complicated than that because we also have memory grow, right? So there could be a concurrent thread that grows the memory while you're reading at the very boundary. So we have to define what happens then, right? So that also has to be ordered. Essentially, memory grow is kind of like an atomic operation. That's the idea. Then, of course, because our memory model is so low level, and you don't declare the type of locations, you just have these different instructions for accessing them. You can have all sorts of mixture in access, right? So you can mix the mode of access, like the same location could be accessed atomically and non-atomically, so you have to define what that means. You can access them with mixed size. You can have overlapping even between accesses because, yeah, there's no restriction on what we can do. And basically what this means is that we have to have a memory model that really specifies everything at the granularity of individual bytes, right? And in some of the instructions you access multiple bytes atomically, but it's still kind of like you see that you're accessing individual bytes essentially. You can also have unaligned access, of course. And then the other, of course, overarching problem was that yeah, we already have this nice formal semantics like small step reduction rules for WebAssembly. And then we do the usual thing of an axiomatic memory model, right? And how do we connect them? Like in something like C, that doesn't matter because there's no formal specification of the language. It's all just wishful thinking and some prose that says, okay, this is how it works. This is not good enough for us, right? We really have to make it precise mathematically. And the way we do that is essentially that the reduction rules become a label transition system. The labels are the memory events that are emitted by these instructions. And then there's an axiomatic layer on top that co-inductively restricts the possible sequences of events that you can observe. But it's still kind of ugly that you have these two layers, and would much rather have like an purely operational semantics, but we're not quite there yet with the state of the art of memory models. Okay, and if you want to see all the gory details, there in our Uppsala paper from a couple of years ago. I'm not going to bore you with those. So to sum up, with WASM 3.0, and again, this is just an aspirational version number, we have generalized further. We now have many modules per store, and modules can be shared. And you have this whole new thing on the side, which is like the heap, essentially, which is another component to the global store. And as you can see, this is a new dimension we're introducing here. And there's this restriction so far that only memories can be shared, right? So the next thing we have to do, and there's active work on that, is after the next release, we want to generalize this to everything being shareable. So that's called the shared everything proposal. And in the paper I just cited, we already kind of defined the general model, but not in the concrete proposal. So the idea there is that this shared annotation is available on all these things and references as well. So you can declare everywhere precisely where something could be observable by a concurrent thread. So it's always explicit in the types whether something can observe concurrency. And then there is the restriction to make that meaningful, that any shared piece of storage cannot point to non-shared storage. So non-shared storage must never be reachable through shared storage, because that could break this invariant that you can only observe threads through shared things. And in particular, that even holds for functions, right? So functions can be declared shared as well, and then you can share a reference to them. But that also means that they can only access shared storage. So it's quite a severe restriction. Like as a picture here, you really have these two universes, and you can have pointers or reference in one direction, but not in the other, right? This is not allowed because it would break that invariant. And what's the point of all that? Yeah, I already said it, kind of like this ensures statically that only shared storage can ever be accessed concurrently. And that is important for at least two reasons. One is that this is necessary, in particular on the web, to have safe interaction with the host. So again, the web is single-threaded, right? So we cannot expose concurrent behavior to anything the outside JavaScript world can see. So this allows us to control what we can pass to the outside based on the types. And there are other host environments which have similar issues potentially. So this is more generally useful. And of course, the other reason why this is interesting or relevant is that to implement the memory model correctly, you sometimes have to insert some fences or other minor things for synchronization, even for non-atomic accesses, because we have to have this well-defined behavior. So there is at least some additional cost attached to using shared memory. But this means that when you use non-shared memory, you don't have that extra cost, right? So the engine always knows where it can optimize away all these extra costs. And of course, the idea is that when you actually compile like a concurrent language, like say Java, where everything can be shared, then you will use shared on everything, right? So typically, you don't really mix these two worlds very much. The main place where the mixture happens is probably at the boundary, like when you're calling into the host or something. And that's also part of what, there's still quite a bunch of open questions here, which I don't really have time to discuss, but one is like, sometimes you really want to escape this sort of trap, right? Especially when you're doing host calls. And then there are lots of open questions about the interaction with other proposals, especially like the stack switching and continuations proposal. And of course, we want additional consistency modes and things like that. Yeah, lots of stuff. Okay, but as my final slide, I guess what I want to show you is like a different rendering of everything well, not everything, but many of the things I discussed. This feature matrix to give you an overview of everything that's going on, right? So we started out with something really simple, but maybe a bit too simple. And then the feature matrix grew and became more regular over time. But we are now finally reaching a point where we get back all the regularity that we want. All the features are available everywhere in the same manner. The feature matrix is much bigger than it was initially, but at least it's regular again. And of course, these paths were kind of very conscious that we took like exceptions to regularity temporarily, because we always knew that eventually we will fix it, but there is some cost involved with that and implementation cost, and we want to ship some features. So for a while, we are fine with doing that. Okay, so there's a lot more I could talk about, but I'm out of time, so thank you very much.
We already had time, but maybe a few quick questions. Please use the microphone in the front here.
Thank you, very, very good talk. So in the your motivation for doing a GC, you said the platform has a great GC, and then you added concurrency, and a lot of those platforms don't deal with concurrency. Do you have a comment on that?
Yeah, so, right, I mean, this is what you see here, right? For the upcoming version, like anything that is controlled by the GC cannot be shared between threads for now. But this shared everything is essentially what gives you that extension later. And you're totally right, especially with web engines. They're totally implemented around the assumption that everything is single-threaded, or at least they used to be that way. From what I understand, they have already moved away from that. And there's actually some movement even in JavaScript to add more concurrency, like concurrent objects. What are they called? Value objects or something like that? You might know that. Yeah, the structs proposal. So, and some of the JavaScript engines are actually already fully concurrent. Like I know that JSC is the Apple thing. I don't know what the status is of V8. So some of the work is already happening anyway, but yes, they definitely have to do kind of re-implement a lot of stuff, especially in the runtime system, not just the GC, but all the APIs are assuming single-threadedness, or used to, right? So that's why we kind of deferred that.
Are there any good examples of languages that either do or could target WASM that have enough of a static delineation of their shared data that they could use both non-shared and shared memories efficiently? Like Rust has this nice send trait, but it doesn't use a separate allocator for shared data. It's all mixed together at the heap level.
Yeah, I mean, as I said on one of the slides, like usually you're either in that world or in that world. I can't imagine any language that makes fine-grained usage of this separation. Maybe there is a good use case for that, but really it's more about the boundary of the runtime, essentially, where you want to make this.
Haskell, you could perhaps put all the pure data in non-shared memory.
Yeah.
The IORFs.
Yeah. Yeah, I mean, I would love to see that, right? If people actually make use of that feature more intelligently, but so far I'm not aware of anybody having tried that or proposed that.
All right, let's thank the speaker again. Thank you, Andreas, for the great keynote. We have a coffee break now. See you all in this room again at 10:40.
And if you're speaking in the next session, could you come and see me? All right, welcome to the first paper session of ISMM. It was great to have that fantastic kickoff in the last session with a keynote, and it was great to see a nice full room. My name's Steve Blackburn, and I'm a researcher at Google and also at Australian National University, and it's my great pleasure to be chairing a session here. And the first speaker we have here is someone who I know fairly well. He's actually my PhD student. Kunal Soren is going to talk. Kunal is a PhD student at the Australian National University, and he's been researching the behavior of garbage collections on mobile devices. And he's going to talk to us about how we deal with memory management on mobile devices. So Kunal, over to you. We'll just let him get mic'd up, sorry.
This one. Hello? Oh, cool. Yep.
All right, thank you, Kunal.
Sorry. All right, so yes, thank you, Steve. So this work was done in collaboration with Steve, Sarah, and Lokesh. And Lokesh is the GC lead at the Android team. All right, so given the ubiquity of mobile devices in our day-to-day lives, a scene like this is sort of unsurprising, of course. And with billions of mobile devices in the world, one would imagine that there's a rich literature on understanding and improving their performance. But unfortunately, it seems like mobile devices are woefully understudied in performance and memory management literature. And that's not because memory management is a sort of solved problem on mobile devices. In fact, if anything, memory management is an important concern for mobile devices given their limited resources like battery life and RAM. So then what's the reason for this gap in the literature? So let's look at this question in the context of Android, the most popular mobile operating system. And so it turns out that there's a variety of factors. So for example, some of the challenges to sound performance analysis on Android are that the Android runtime primarily only maintains some production garbage collectors. So some simple baselines to need to calculate overheads, which we'll discuss later, they don't really exist. And given the highly multi-tenanted environment of a mobile device, we often have many apps running at the same time, all vying for the same set of resources. So it's actually difficult to define a sound experimental methodology. And also, realistic applications are hard to control, both from an automation perspective and a technical perspective, as we'll see later. And these are just some of the issues plaguing sound performance analysis on mobile devices. And you can imagine how a lack of a sound methodology can both be a cause and a consequence of this gap in the literature. So I'll quickly give a brief overview of the Android architecture and some key background knowledge required for the rest of the talk. Android is a multi-tiered architecture based on a Linux kernel, but what we're interested in is the Android runtime, which runs all applications, essentially. So starting an app on Android is actually quite different from a standard Linux machine, and that's because Android has a special process called the zygote, from which all applications are actually forked. So let's say a user clicks on an app in the launcher. The launcher then asks the activity manager to start the application, which then asks the zygote to fork itself and specialize the application. So in this way, the zygote is actually the parent of all Android apps. And this allows the Android runtime to preload common libraries and classes into the zygote with twofold benefits. You get faster app startups, and you also reduce memory consumption due to the copy on write nature of the zygote. But this actually complicates performance analysis. Since all applications are forked in the zygote, they share the zygote starting parameters, which includes heap sizes, type of GC to use, etc. It's actually quite difficult, or it's actually not really easily possible to change the heap size of an application like you would do in Java by just changing the command line arguments. And these are only some of the issues we face while trying to come up with the sound performance methodology, or performance evaluation methodology on Android. So switching gears a bit, how do we even measure the cost of GC? Well, so in our work, we use this methodology described by Zishin, who is here somewhere? I don't know. Zishin and co. In this ISPAS 2022 paper called the ELBO methodology. And just to be on the same page, I'll quickly go over the key points of this methodology, but I would highly recommend checking this paper out if you haven't read it already. So a simple, straightforward approach of measuring GC cost is to just sort of demarcate the start and end of a GC, like we've done here in yellow, and measure the cost in between, where everything else is assumed to be the cost associated to the mutator. Unfortunately, we know that that reality is quite nuanced, and that's because some GC cost is hard to separate from the application costs like allocations, read and write barriers, concurrent GC, etc. But the idea of the methodology is, what if we have a magic GC, which essentially has all the benefits of the best GC without all the associated GC cost? Well, in that case, then we could run the application using this magic GC and then measure its total cost, and then use this total cost to calculate the overheads of the rest of the different systems. Right? But unfortunately, we don't actually have this magic GC, so the idea of the methodology is to try and best approximate it. So a key requirement of this approximation is having simple baselines which have clearly attributable costs and very few hidden overheads. So I've essentially skipped over the detailed steps of how do we calculate this method, this approximation, but in the end we get something like this, where the regions shaded in red are considered to be the empirical lower bound on the cost of each of these different collectors. And the cool thing about this is that the methodology is both language and metric agnostic. We could have been doing this in Java and Python, and we could have been trying to measure walk clock time, CPU cycles, power, etc. Solver has 4 key requirements. And the first one is we want to have the ability to cheaply and reliably gather key metrics like GC time, CPU cycles, etc. We also want to have a way to reliably and repeatedly measure workloads in order to increase statistical significance of results. And we want to have the ability to attribute cost explicitly to the GC itself. And like I mentioned before, we want to have a well-understood and simple baseline, which minimizes meter overhead as it helps better approximate the quote-unquote ideal GC. So I'll go over some of the major challenges we faced while benchmarking under applications, but in the interest of time, I'll only discuss these 2. So since all applications are forked in the zygote, they share the same heap size arguments that the zygote starts with. And this means that if we want to change the heap size for an application, we have to do it globally. And this may not even be possible if we, for example, if we set the heap size to something which is too small, then the device might not even boot. And this is unsatisfactory, of course, because GC being a time-space trade-off, we really want to be able to control space in order to see what happens to time as we vary space. So what we do is we hijack the application specialization process to set the heap limits. And so after an application is forked from the zygote, it actually has to set up many things before the application can even start. So we insert a check here to make the application install a metadata file, which essentially lists heap sizes for target applications. And if this application finds itself in the list, then it'll set the heap size to what has been specified in the file. Otherwise, it'll just do whatever the default is. And so this allows us to target specific applications without affecting the rest of the system. And since we can update the entries of this file at runtime, we can choose to target any application with any heap size at any time without recompiling or rebooting the system. So one of the most difficult challenges we faced was the tendency of Android applications to introspect their own heap usage. And they do this for a variety of reasons, such as they want to resize software caches, or they want to preemptively call a GC before the heap is full, etc. But this is problematic for us because the benchmark can actually is essentially dynamically altering its own behavior, and also it sort of breaks assumptions we have about having fixed workloads. And so to mitigate this, we intercept some standard Java APIs to return a false but consistent view of the heap back to the application. And this means that this should mean that the application's behavior is invariant to the actual heap size that it is running under. However, it's not a complete fix, as applications can still view their own heap usage, by using JNI or some other third-party library that we haven't mocked. And the best fix, of course, would be to edit the application source code to remove uses of this heap introspection. But unfortunately, this is not possible for the majority of Android applications since they're closed source in nature. So we also benchmark some standard Java workloads, so workloads on the phone. And for benchmarking these, we adapt some sort of standard state-of-the-art benchmarking methodologies from the server world. And we also for these benchmarks, we also further implement some simple baselines like no GC and optimize the existing semi-space implementation, like we'll see later. So now I'll talk about one of the other key contributions we have from our work, which is the curation of a benchmark suite consisting of real-world Android applications. So benchmarks are an incredibly important but often overlooked aspect of our field. And without such suites, we can often fall into the trap of using micro benchmarks or ad hoc benchmarks, which makes comparing performance across different studies quite difficult. And Android has many benchmarking suites, but most of them aim to test hardware or micro benchmark performance. And importantly, all of them are closed source. They don't use any real-world applications, and also they have opaque testing criteria. So in our work, we curate a set of Android benchmarks using real-world applications, and we make it publicly available. So since all Android applications are highly interactive, we need to be able to script user interactions in a deterministic and reliable way. So what we do is we use the UI Automator library, which is an open source library maintained by the Android team, to interact with UI elements. And this library was designed with black box testing in mind, which is great for us because we don't actually often have access to the source code for many of these real-world Android applications. It also allows us to be a bit clever. Like, for example, it allows us to wait for animations to complete, like waiting for a button to appear or disappear, instead of just doing fixed waits like we'd have to do otherwise. It also allows us to directly interact with UI elements instead of requiring the exact XY coordinates of a particular button or a text input, and also allows us to search for elements which are currently visible on the device screen. But this does come with some downsides, and that's because now we actually have two ARC instances running at the same time. And the first one is the application itself that we're trying to measure, and the second one is the benchmark harness running UI Automator code that is essentially sending input events to the target application. And this is not ideal, of course, because we've increased the amount of variance in the system, but it's unfortunately the only way we were able to do this. So we curate a set of 10 popular real-world applications with realistic workloads over a diverse variety of use cases. However, we omit two notable use cases, web browsers and video games. Web browsers and similar applications would be predominantly JavaScript benchmarks with a very thin Android Java layer. And video games are much the same, as they often directly allocate into the native heap, or they use a game engine like Unity. So we faced many issues when trying to build this suite, but in the interest of time, I'll only go with this one. So benchmarking can still be quite flaky even when we're using UI Automator, and that's because dynamic content displayed by applications like Facebook and Twitter is actually quite problematic. And that is due to different layouts can actually have different allocation behavior or benchmark characteristics. And what I mean by that is, for example, you can consider something here like we have here on the left, which has a series of videos together. You can imagine that this is doing more allocations than something what we have here on the right, which is just a sequence of static images. And I'll show some results later which sort of corroborate this. So like I said before, we also use some standard Java workloads, and we benchmark them. So we use a subset of the Da Capo 912 benchmarks, and we also use GC bench, which is just a simple micro benchmark. And obviously, this is not realistic in a sort of mobile setting, but this allows for comparisons to similar studies to OpenJDK, and also allows us to understand core garbage collection performance. So we use two different devices in our experiments, but for the rest of this talk, we're only going to be discussing the Pixel 7 Pro results. And this is a picture of the actual experimental setup, which is sitting back on my desk in Australia. So I'm not going to go over the entire experimental methodology, but the key idea was that we tried to remove and reduce as many sources of noise as was possible. And I would recommend checking our paper out to see what other stuff we had to do. So these are the results for the vanilla Java benchmarks, but in the interest of time, I'll only go with this one. And so first, let me explain how do we interpret the graph here. So on the x-axis, we have the multiple of the minimum heap size for this particular benchmark. In this case, 1 is 18 megabytes, and 6 is 108 megabytes. And on the y-axis here, in this case, we have the task clock overhead. And the closer you are to 1.0, the closer you are to the approximation of the ideal GC. So this graph is actually quite interesting. As you can see, that our semi-space implementation, optimized semi-space implementation in light blue actually performs much better than the stock one. But what's also interesting is how the concurrent copying collector performs much better at smaller heap sizes than at larger ones. And we find that this is because it actually reduces cache misses due to more frequent GCs for smaller heap sizes. So now these are the results for the Android applications. And what we've done here is we've taken the geometric mean of the task clock overhead, in this case, across all the different benchmarks, excluding Twitter. And these results are sort of unsurprising because we can see that for smaller heap sizes, the two concurrent collectors actually have higher overheads. But what's also interesting is how the semi-space collectors have similar overheads to the concurrent copying collector at larger heap sizes. So now these are results for two of the Android benchmarks. On the left here, we have Airbnb, which sort of behaves like you would expect with smaller heap sizes having larger overheads and so on and so forth. And so you get this nice curve. But over here on the right, we have Twitter, which sort of behaves very chaotically, and there's no sort of visible trend here. And we believe this is because that Twitter is actually quite sensitive to the layout of posts, which are currently visible in the timeline. And you can see that each point actually has the error bars actually quite tight, suggesting that the results are quite reproducible within a particular heap size, but they're not quite stable across the entire range of heap sizes. And we believe this is because that each points are actually measured in different moments in time, so a different set of posts is currently visible in the timeline. So these sort of Twitter results underscore how difficult it is to come up with the sound performance methodology for, yeah?
Oh, sorry to ask a clarifying question.
Yeah. Okay, sure. Sorry. These sort of Twitter results underscore the difficulty in trying to come up with a sound performance methodology using realistic applications with realistic workloads on a mobile setting. Okay, so in conclusion, we've identified challenges and pitfalls to sound performance analysis on Android. And we've also outlined a small benchmarking suite consisting of real-world Android applications with realistic workloads. And we also find that for a modest heap size, production RGCs have lower bound overheads at around 2 to 51%. All right, thank you.
Great. We do have time for a couple of quick questions.
You made some comments about dynamic content, and I guess what really confused me was scrolling through Twitter, we're seeing different posts on every single time we run the benchmark. Are we doing record and replay of the server-side traffic to pin that between mobile runs or anything like that?
Right. So yeah. So there's a whole bunch of stuff I had to cut out from the talk in the interest of time. But essentially, what we're doing is we try to limit network traffic in a bunch of ways. And one way we do it, we limit the set of the set of accounts which we follow, right? So we then only go to the followed feed, and then, for example, you would only theoretically you should only see chronological updates to that timeline.
Got it. But this benchmark is using real live internet content. So
Yes.
you
Yeah.
want to run it all at once before things change too much.
Yeah. And so that, yes, exactly.
Okay.
Any other questions? Yep.
Can you please use the mic? Thanks.
Which slide, sorry?
The very first slide, the results.
Oh, very first slide, the results.
Yeah.
This one?
Yeah. Why is that orange color going up with the increase in heap size?
So like I mentioned before, you mean this one, right? Yeah, so like I mentioned before, it's because we find that this, over here, you're actually reducing the number of cache misses due to increased GCs for smaller heap sizes. So you actually have better cache utilization, right? Which is an interesting result, right? You would expect smaller heap sizes to have larger overheads.
Since you're already on that slide, can you also clarify why the yellow line starts at me?
Okay. Right. Okay. So this is no. This is essentially an artifact of how Android essentially considers what is heap size. So, like in a normal runtime like Java, whatever you set on the command line, like XMS and XMX, that's the entire memory that is available to the collector. So like a semi-space, you would actually only have half of that as from space and half of that as to space, right? But in Android, whatever you set as the command line argument essentially is just the from space, right? Oh, sorry, it's just the to space, and the from space is quote unquote free, right? So that's why the two copying collectors, the concurrent copying and the semi-space, we've shifted them to write by 2, But the concurrent Mark compact collector, which is just like a simple concurrent, it's not simple, but it's essentially a concurrent Mark compact collector, so it only has the two space, right? So it's an artifact of how art deals with memory. All right.
All right. Well, thank you very much,
Thank
Kunal.
you. Oh, sorry. Yes, of course.
Unfortunately, as so often seems to be the case, our next first author could not make it here because of visa-related issues. But we're very lucky to have Ryan Newton present the talk on their behalf.
All right, yeah, so my former PhD student, Chaitanya Koparkar, is the first author on this slide when it appears. Here we go. So this is the latest chapter in our work on a very unusual compiler for a subset of Haskell. All the people in this room who work on language implementation, maybe with a focus on the runtime system and memory performance, know that data representation is extremely important. It's at least as important as all the work we put into transforming code to make it more efficient. If your compiler uses an inefficient data representation, you're kind of hamstrung from the start. So coming back from ICFP 2016 in Japan, I think, I was just feeling very upset with pointers. Pointers are littering our heap everywhere. And all our language implementations, pretty much without exception, use at their base the kind of simple runtime layouts that Andreas was talking to us about this morning. So they've got structs, they've got arrays, they've got numbers, right? But those structs are always small heap objects, and they're always connected by pointers. So like the picture up at the top here. So this is what I would consider a fully pointer-based representation of something like a tree. It doesn't matter if it's Java, OCaml, Haskell. It's all, there are small differences, like what is the layout of the object? Do you have, how big is the header on the object, and so on. But overall, the basic idea is the same. And at the other end of this spectrum that I'm picturing here, there's fully serialized representations, the kind that we might write to a disk in a binary format or that we might send over the network when we want to be really efficient with space. So this experiment, this Gibbon compiler that I'm talking about today, is somewhere in the middle here. We try to, as often as possible, use the very dense representation as our de facto heap representation for all algebraic data types that the compiler uses. So there's a lot of magic in the compiler that goes into making that happen in terms of figuring out how to co-locate multiple heap objects together and allow them to be as small as 1 byte. So these individual heap objects here are 1 byte wide. They're essentially just a tag. So this is node, leaf, and so on. But the topic today is about garbage collection in this world. And the reason you need garbage collection is that the whole memory, unlike one of those WebAssembly modules, we can't just have a single flat array as our entire memory. We're compiling a higher order program that we start with, and there are many values in the program, and there are reasons that pointers sneak back in. So even though we bias everything towards serialized, we end up only mostly serialized, and we still need to garbage collect. But our ideal, of course, if we're doing something like a tree traversal, our ideal is to do linear sweeps with nice, predictable memory access patterns over these buffers. And this is true both in allocation and in reading data. So even if you start with a high-level program, like a Haskell program that traverses a tree, what you end up with at runtime, it maintains a single pointer into a buffer that you're allocating into, sweeping from left to right. And then when you read the tree, you're doing the same thing, reading from left to right. So to give a sense of the motivation for this, like why do we go to all this trouble to have a very exotic data representation? It's because if you're processing things like HTML data or program representations inside a compiler, if you're doing tree traversals, this makes a huge difference. And I'm always, microbenchmarks get a bad name, right? We'd rather have our real Android application benchmark suite. But I also feel that microbenchmarks can be very educational. It's interesting to me that you can take a simple program that traverses a tree and get 2 orders of magnitude difference from different compilers with basically the same source code. So this is a plot from our eCoop 2017 paper on this Gibbon system, where we showed that this simple kind of tree traversal, even your kind of your basic C code is going to be 7x slower than what you can get if you use the denser representation. And that's why Gibbon here is leading the pack in this particular shootout of compilers. Things get complicated when you move away from doing these bulk traversals. So bulk traversals are great because I process the whole tree coming in, and I produce a new tree coming out, I transform it into that left to right sweep over a buffer. But we're compiling these arbitrary functional programs, so we have to deal with programs like this one, which takes a tree as input and wraps just one extra node constructor around it, which ends up being either a deep copy, which would be very inefficient. We take a billion node tree and we want to add a leaf to it, so we copy all billion nodes there and add one leaf to the front of it. That's obviously a no-go. It changes the asymptotic complexity of the source program. The programmer would be very unhappy. So we're forced to reintroduce some notion of indirection. We want to do a constant size small allocation. We want to introduce back a pointer that points to this other pre-existing data. So you'll notice there's a little extra tag here, and that's because as we read these byte streams, we expect the default be that all data, all scalars and other data constructors be inlined in the byte stream. So it's kind of the exceptional case. It's like an escape code to say, OK, now we're actually going to have an indirection, and you have to redirect the byte stream somewhere else. So that's what our pointer looks like. And actually, inside our compiler, we do transform the algebraic data type to have an additional constructor for this indirection. So when we're pattern matching on this data type, handling the pointer case is just one more case in our switch statement that deconstructs that data. The first version of Gibbon, like in that 2017 paper, used region-based memory management exclusively. So we hadn't yet gotten to having a garbage collector, which is what the present work is about. So in region-based memory management, for those of you not familiar with it, you have lexically scoped regions into which heap objects are allocated. Famously, the MLKit compiler did this. Our version of region-based memory management is actually a bit of a compromise because we allocate all regular functional data into these regions, but we allow data to escape regions as well. So region X, as in our example where we're adding to a tree, if we add a pointer to an old pre-existing tree, that would be, for example, region Y might point to region X. We actually allow at runtime pointers between regions and regions to keep other regions alive. So regions in our lingo become the chunks that we allocate into. And our first version of memory management in this exotic compiler setting was purely reference counting based. So we would have these chunks of data, which would usually but not always contain multiple heap objects, and they would be reference counted. The pointers between them would be, therefore, be the references that we were counting. So the way we implemented this would be, here's two regions. One has reference count 1, one has reference count 2. We would track the outgoing. We'd actually track the full set of regions that are outgoing from the full set of outgoing pointers, and we'd remember those for various purposes. And we try to maintain this fast path stack style allocation, where if you allocate a bunch of data into regions with let region, and then they are actually free and not escaping by the end of their scope, you just deallocate them immediately. But if they persist longer, then they'll only be deallocated later when their reference count drops to 0. So this is fine if you don't have that many regions, if you're doing bulk traversals on them, and if your number of heap objects per region is fairly high on average. So that's why when we're doing bulk traversals over tree data, we achieve a 2.3 and a 1.5x geomean speedup over GHC and Java, respectively. But we initially in this project were focused on the strengths and not enough addressing the weaknesses of this approach. So the weaknesses of this approach is, of course, if you write programs that do many tiny small allocations, then we basically are a under-engineered, poor version of a memory system that compares fairly badly with a 7.4 and 3.1 GX geomean slowdown compared to GHC and Java. So the purpose of this paper was to kind of reintroduce and adapt established memory management techniques to be able to claw back some of the benefits for these small allocation programs, not necessarily to exceed there, but to mitigate the weaknesses while keeping the strengths. And there are also some other disadvantages to using this reference counting approach that I mentioned before, and I'll get into those a little bit in a minute. Our kind of poster child for a program that behaves very badly under this purely reference counting region-based regime is reversing a list. So if you, for example, do an insert into a tree, at least you get log in new nodes within the region that you allocate. In this case, you only get a single con cell, worst case in every region. And the reason for this is if you can imagine, if any of you are familiar with the way region-based allocation works, you've got a cons here, a cons expression that's being passed to the recursion. And when we infer regions and insert let regions in this program inside the compiler, we're going to end up allocating a new region here. And that new region, for every single con cell, will point back to the result of the reverse. You can imagine a sufficiently smart compiler trying to do reverse in place inside one buffer, but it would be very hard. We'd have to have regions that grow from right to left as well as left to right, and you'd have to know exactly the size of the list in advance, which we don't do. So currently, Gibbon will end up with this fragmented result from a reverse. So if you take an input which is compact and serialized in the way that we like it to be, running reverse on it will give you this memory representation. You'll actually even have this little extra pointer, this little extra header object at the beginning, which isn't great either. And that's kind of because of our destination passing style conventions internally. Anyway, you'll notice in this case, we have a number of disadvantages because now we're wasting extra space on these little indirection tags as well. So we really want to avoid this as much as possible. And you can see here we're 3.5x slower on reversing a list than GHC, 2.75x slower than Java. So our goal for this work is, again, mitigate those weaknesses. And we do that in the tried and true way of introducing a generational collector. And we keep that reference counting system as our old generation. We insert a new copying collector as our young generation. So that basically gives us a lot of the advantages of copying collectors, except they work out in a slightly different way in this region-based environment that I'll show you about. So first, I mentioned it's largely traditional. So this means we're bump allocating into a nursery. The nursery is one big space here. And what we're bump allocating are essentially little mini regions. They could be as big. In some cases, we statically infer their size, and we say this is one con cell. In some cases, they're kind of a minimum size, like maybe they're a kilobyte. And we expect multiple regions, multiple objects to go in them, but we don't know how many. We need a lot of dynamics. We need to handle a lot of things here that are unusual. For example, our objects, if you think of these little regions as objects, they grow. And so you might allocate a small region, allocate some heap objects into it, some individual values, then have it overflow and need to grow in some way. So that complicates things. And so you can see in the paper there are various strategies for eagerly promoting when you need to grow a region and so on. Now, once things get collected to the old generation here and we evacuate, there's a number of beneficial properties to this. But one of them is simply that you of course, get the usual locality benefits from copying, and you eliminate things that have died and all the normal kind of exploiting multimodal lifetimes, as we've always done in generational collectors. But you also get some unique benefits that I'll highlight in a second. But first, let me tell you a little bit about how this GC works. The GC is largely traditional, I mentioned, but evacuating here has a couple of special concerns that you can check out in the paper. One of them is that you want to make sure to sort your root set so that you try to keep the data that's copied to the old generation as much in line as possible. If we reverse that list and then we evacuated it in the wrong order, we'd end up with the same fragmented representation. We want to reverse it. We want to garbage collect the reverse list in a way that it ends up back in a compact in-order form. So the punchline with that reverse microbenchmark would be that you would still within the nursery create the individual con cell allocations. But then if the reverse list lives long enough, it will be evacuated to the old generation. It will be back in a compact form. And you can check the paper for the details of how we sort the root stack. And the upshot of all this is that our new collector has a number of unique benefits here. It's got the old standard benefit of efficient bump allocation in the nursery that everybody would expect. But it's also got this kind of extra strength benefit of compaction. So it's not just the normal locality principle of copy and collection where we put objects close to each other. It's the extra magic benefit that when you put them close to each other in the right order, they get much smaller because the pointers disappear. So that we feel is an extra strong motivation for using this architecture in this exotic scenario. But there's also a number of challenges that we have to overcome in order to adapt these traditional copying collector and generational collector techniques to this unusual environment. So one is just that we're very cramped. So these objects do not have a full header word. They are not aligned on a word boundary. We in part, this approach is efficient because it's utilizing the efficiency of unaligned access on modern architectures. We have all these 1-byte objects floating around, which means that the 4 and the 8-byte objects are not aligned. We've got sort of a soup of bytes as our representation. And in that world, you don't always have space for a forwarding pointer, which the people in this room are probably familiar that forwarding pointers are often used during garbage collection to remember that you've already relocated something so that you don't make an additional copy of it during garbage collection. So you can check the paper for how we handle that. We also have a lot of weird pointers into the middle of packed data structures. If we're talking about Java, you're used to an environment where you've got a graph of pointers, but they are polite enough to point to the beginning of the object instead of pointing right into the middle of your object at some unaligned byte offset, as we often do. We also collect these partially written objects. You'll be halfway through allocating a tree, garbage collection is triggered. Now we need to relocate everything, including this kind of raw open end of the half-written object, which needs to continue allocating after you've collected. So those are some of the challenges that we address in the paper. Oh, little animation there. Here is the summary of the benchmark results you'll see in the paper. So we split our benchmarks here into two different qualitative sets. So one of them is these small allocation benchmarks. These are the ones where we expect to have a radically different performance with the GC-based version of Gibbon. And the other ones are kind of our traditional benchmark set of large traversals over data, where our goal is to just hold the line. If we can keep the benefits that Gibbon already has, we've done our job there. And we basically accomplished that, where we sped up by 3.39x on the small allocation benchmarks with our new techniques versus our old one, while holding the line on the other techniques, or on the large allocation benchmarks. Then, of course, we also compare against the Haskell compiler. We're still half as fast on small allocation benchmarks compared to GHC, which has been very well optimized over several decades for this kind of class of functional program that does many small allocations. In fact, Java doesn't do quite as well on those small allocation programs, so we're already on par with Java on the small allocation programs. OK, I mentioned those three challenges. I'm going to wrap up here, but I want to give you a little bit more detail on one of those three challenges. So how do we maintain sharing in the presence of these cramped and unaligned layouts? I mentioned that we don't have room for just unconditionally having a forwarding pointer, so we had to come up with some slightly new techniques here. You could actually forget about the forwarding pointers. Forwarding pointers are destructive. They go kind of in place of the object that you're relocating. You could do everything inside metadata off on the side, but that gets really expensive really quickly, especially when you're trying to deal with billions of very small objects efficiently for these bulk data applications. So our solution is to basically optimistically stick a forwarding pointer wherever we have room. If I see that your object is 9 bytes or more, then including that little header tag that's 1 byte, then I will go ahead and place a forwarding pointer. During evacuation, if you land on something that is too small to have a forwarding pointer, we have some additional logic that allows you to scan to the right. And then we need to maintain a global invariant in the system, which is that if you land somewhere in the heap and you look for your forwarding pointer, you will be able to find something to the right that will enable you to figure out where you need to forward to. Here's a particular example of that, just to make it concrete. So we are relocating these dense objects into the old generation. We go ahead and we copy over some data. When we have the space, we're going to overwrite our data with the forwarding pointer. And when we don't, we're going to use this scanning logic. So we finish that initial evacuation. But now there's this other region over here that we haven't evacuated yet. So when we come along to evacuate this region, we want to copy that initial tag. But then we want to follow the indirection. Now, of course, we don't want to copy indirections willy-nilly. Our goal is to get rid of those, not to maintain them in the old generation, right? So we want to instead kind of inline the data and keep following the indirection, subject to maintaining any sharing in the heap, because we don't want to duplicate data. So when we get over here, we need to do a little math. We need to figure out, OK, well, this is actually pointing to a byte that is not itself a forwarding pointer. But if I scan to the right, I can find the forwarding pointer, and then I can do a little math to figure out the address of the thing I actually want to point to. And then I could write an indirection over here to byte number 601 after doing that math. So you can check the paper for the full algorithm and the details there. But the end result is that you eliminate, we have a theorem that the number of indirections post-garbage collection is the minimum that you need to maintain the sharing in the original heap with no additional indirections beyond that. OK, so that is it. Our future work in this area is basically this is our first step into memory management for this system. We've introduced this copying collector in our young generation. And we have a lot more work to do to improve our collection in the old generation and so on. I'll leave this up while you ask any questions if we have a minute.
Thank you, Ryan. Great talk. We have a couple of minutes for questions.
identify if something is a forwarding pointer or not? Does it depend on memory alignment, or how do you find out?
Yeah, so we've got this basic scheme here with any of these data types where there's the tag that represents which kind of object it is, and we're switching on that tag. And we just allocate special tags for these things. So we have a special tag that we use for indirection, and we have a special tag that we use for forwarding, and we have a special tag that marks this byte has been copied, but it's not big enough to have a forwarding pointer. So when we're going through and evacuating, we have a switch statement over these tags, and there's just one case that handles this and one case that handles this.
Tag because the bit set in the word or in the byte?
The tag is always 1 byte in our current implementation. So we only have 256 of them. Yeah. But of course, you could always use a variable width encoding for that if you wanted to support data types with more than 256 variants, which do pop up a fair amount in practice, especially in automatically generated code.
Any more pressing questions? Oh, Tomorrow.
For the copy PLDI, what if all the elements are too small to contain or to be overwritten with the forwarding pointer?
Sorry, so what if there's not enough room to maintain the forwarding pointer? Where exactly?
Yeah, so in this case, there are
There's sort of a forwarding, there's room for the forwarding pointer right after it. So I think you're going to kind of the worst case scenario, which is imagine that we've got a series of heap objects that are all 1 byte. It's like you never bothered to have a scalar. You only have a tree that is consists only of the structure of the tree, for example. You could have megabytes and megabytes of only 1 byte objects. So in that scenario, we do have some kind of fallbacks where we go to this side metadata table. But keep in mind, though, I will mention that if you're looking at a chunk of sub-word sized objects and none of them are yet forwarded, you can actually, in some cases, insert a forwarding pointer if you know that there are not any incoming pointers that are subdividing that particular span of 9 bytes. So there's a lot of kind of corner cases to get into there. But we just don't expect we hit that situation very often. Because there's usually kind of enough space, often enough, in any realistic data that you can fit in at least some forwarding pointers. And just put most of the load on those forwarding pointers rather than on the side metadata that we have to fall back to. But good question, thank you.
All right, thank you, Ryan. Sebastian, can you hear me?
Yeah, hello.
Oh, we
yeah,
don't, we
don't
don't,
know
we
what
don't hear
happened.
you just yet. Just one moment.
Hello.
One moment. Okay, now we see your screen, and can we do another quick audio check?
Hello.
Oh,
Now can you hear me?
You're still silent. One moment. We see you fine, but can we just check the audio one more time?
Okay. Now can you hear me?
You still have no sound.
Okay.
While we wait for the audio, I think Sebastian can hear us. Can you hear us, Sebastian? Can you give me a nod? Yeah, he can hear us. So
Yeah,
while
yeah.
we're waiting for his audio, I'll just introduce him and introduce the talk, and we can pipeline that with the audio fix. So Sebastian Montano is an engineer and a PhD student, and he's the first author of this paper, which is about evaluating finalization-based object lifetime profiling, which I'm going to be interested to hear about, because I remember at ISMM in Tucson, I think it was, Tim Harris giving a really interesting talk on this many years ago, on something related to using the finalizers to do lifetime profiling. So there's a nice long history here at ISMM on such subjects. So I'm very much looking forward to hearing Sebastian's talk as soon as we get the audio sorted out. Yeah, Sebastian, can you try again? Nothing. We have the tech team working hard to fix the problem. So yeah, I was going to make the same suggestion. So it seems like the issue with Sebastian is at our end, not at his end. And I think in the worst case, we just hold some device next to a microphone and let it go. I think we're just having problems switching his audio through to this room. Oh, now we have a feedback loop. All right, can we try one more time? Sebastian, can you just say a few words? Yeah, just a little quiet. Hang on. We'll just get the volume. Can you just say a few more words to test, and we'll just get the volume right?
Hello, can you hear me?
Yeah, that's great. We finally have you. Now, one minute before you say another word, we'll just get your video right. We had the video before, but we'll just bring the video back on the screen. I think we are now all ready to go. So thank you everyone for your patience. We now have Sebastian, we have video, and we have audio, and we're ready to go. So thank you, Sebastian.
Thanks to you. Well, welcome. Hello, everybody. My name is Sebastián Jordan Montaño, and I am here to present our paper, Evaluation Finalization-Based Object Lifetime Profiling. So let's start. Let's quickly start about discussing about context and description of the paper. Well, first, we know that object lifetime information, it can be very useful for applying memory optimizations, such as pretending objects like they can live a long life, or to check the garbage collector parameters to optimize performance. And one way of developing these profilers is through finalization mechanism. This is a technique that it was used in the past, but it was not evaluated in depth. But in this paper, we are going to focus on this. If we want to use finalization to do object lifetime profilers, this is the way to do it. First, we need to capture the allocation time. And this is done through code instrumentation. We can instrument the parts of the code where allocations are produced. And at each time that allocation is produced, we capture this allocation time. And then with finalization, we can capture the collection time. And with these two things, we can estimate object lifetimes. One challenge of doing this, but however, this can have advantages and disadvantages. For example, one advantage is that these mechanisms are normally already presented in runtimes in virtual machines, so we don't have to implement it. But one challenge, it can be, for example, we can have a delay lifetime observation. For example, if we look at this timeline, we have a time 0, the object allocation time, in which is the time in which the object is allocated. Then, after some time, the object becomes unreachable. But it's only after some delta that when the garbage collector or memory management is traversing the memory, in which it detects that the object is unreachable, and then it starts to prepare the object. And then, after some other delta, is when the runtime is actually finalizing the object, and is when we are taking the measurement. So, as we can see in this little graph, we can see that there is a delta between the actual or the real lifetime and the estimated lifetime. And this delta, it can be as big or little, but we cannot know this in advance. And another challenge, it can be the contamination. Well, in this paper, we focus on ephemerons, that ephemerons are one way, one finalization mechanism. There are others, but in this paper, we study ephemerons. And basically, how do they work is that at each time that we allocate an object of interest, we allocate also an ephemeron, and the ephemeron knows its object. And then the garbage collector detects that the object of interest is unreachable. It puts it into a finalization queue, and then after some time, also the runtime actually invokes the finalization callback to finalize the object. So this can contaminate the heap, adding extra garbage collection pressure. So the goal of this paper is to first to understand the impact of the ephemeron contamination, and then also to understand the impact of the delay observation times. For this matter, we developed Philip. Philip is a finalization lifetime profiler that we built for experimentation. It tracks allocation time by instrumenting allocations. It tracks collection time with ephemeron finalization, and optionally also it can pretend the ephemerons for experimentation. We are going to discuss this point later in the presentation. And finally, it has a built-in sampling support that it can track a configurable subset of all allocations, like the developer can specify the sampling rate of the or the percentage of the allocations that wants to capture. So now I'm going to pass to the methodology and the results. In this paper, we study 4 research questions that are the first one is our lifetimes, are the lifetime that we are estimated are actionable. The second research question is how does sampling impact the computed object lifetime? This question aims to study the precision. The third one is, does sampling reduce the execution time overhead? And finally, we have if the sampling reduces the memory overhead. For time constraints, we are only going to explain the second and the third research question in this presentation. But if you are interested, please, you can have a look at our paper. In our paper, we have the 4 questions detailed. As the benchmark selection, we selected these 5 applications. There are, well, first we have data frame. Data frame is a tabular data structure for doing data analysis. Honeygr is a physics simulator. Moby Dick is a multi-agent simulator. Also, we have a Block that is a low-level UI framework. And finally, we have Moose. Moose is a platform for doing software analysis. And as the general methodology, what we did is we profiled each benchmark using 4 different sampling rates, 0.1, 150, and 100%. Also, when the results are presented relative to the total execution time, this is to account for the profiling overhead. Instead of saying that the lifetime will be presented, for example, instead of saying leave 1 or 2 seconds, we will say that leave 15% of the total execution time. And finally, also the execution time overhead will be presented with and without ephemeron pretendering. So for the first research question that I will present in this presentation, that corresponds to the second research question of the paper, we have the methodology. What we did is we compared the estimated lifetimes across all sampling rates to assess the degree of variation between them. And also we present an in-depth analysis of the data frame benchmark. It is worth to note that even though if we only present in-depth the data frame benchmark, we obtained similar results for all of our 5 benchmarks. So first, we have this table. First, let me explain this table. In the rows, we have each of the benchmarks, each of the 5 benchmarks. And in the columns, we have the overall average lifetime for the 4 sampling rates. And in the last column, the one in the right, we have the average with the standard deviation. So for example, if we can see the data frame example, we can see that for 100% sampling rate, we have an overall average lifetime of 15%. So the overall average, it says that the object leaves 15% of the total execution time. And in the other extreme, we have 14.2%. So if we go to the last column, we can see that we can observe among our 5 benchmarks that there is no such a big variation between the estimated lifetime across all the sampling rates. We can see that there's a small standard deviation, except for the Honey Ginger and Moby Dick, and we can see that for Honey Ginger the standard deviation is 15%, but the estimated lifetime are really small. We can see 0.09, 0.05. So we have a big standard deviation, but still the estimated object lifetimes are really small. And for the data frame case, for the in-depth analysis, we have these histograms. First, also let me explain. In the top part, the first 3 rows, we have the short-lived classes, in which each histogram represents in the y-axis, it represents the percentage of objects, of allocated objects. And the x, we have the relative object lifetime. So, for example, we can see for the class function, the first one in the top, for 100% sample rate or even for 0.1, we can see that 100% of the objects, more or less, they have a lifetime close to 0. This is the case for all the 3 short-lived classes for all the 4 sampling rates. And for the other example, for the long-lived classes, we have the opposite behavior. We have, for example, we can see the byte string class. They have like 100, almost around 100% of the object that they live close to 100% of the execution time, so until the end of the execution time. And similarly, we can observe a similar behavior for all the 4 sampling rates also. So as a conclusion for these research questions, we can see that we can observe consistent lifetime frequencies, and this suggests that our profiler gives precise measurements. As a recommendation for developers, we recommend developers, if they want to use such a profiler, they can start with a small sampling rate, and they can gradually increment it if needed. We obtained precise results using a 0.1 sampling rate. Of course, this also depends on the application that is going to be profiled. And for the second research question that I will present in this presentation, that the third one in the paper, we're going to study the execution time overhead. As a methodology, we did a comparison across 5 configurations. First, we have the baseline, that is the execution time without the profiler. And also we have the execution time with the profiler active with sampling rates of 100%, 50, 1, and 0.1. These are our 5 configurations. And also in these research questions, we studied the effect of pretenoid in the ephemerals. For that, we have this table. But first, also let me explain quickly the table. In the rows, we have the benchmarks. For example, in the first one, we have data frame minus pretenoid. This minus means without pretenoid, and the plus with pretenoid. And also we have the delta. So the delta is the difference, the overhead difference between the with and without the pretenoid. So as we can see that pretenoid in the ephemerals have a positive impact across all 5 benchmarks and across the 4 sampling rates. As an extreme example, we can see the one in red, that for the Moby Dick benchmark, we managed to improve or to reduce the overhead by 15 times by pretenoid in the ephemerals. And so, as a conclusion, we can see that pretenoid in the ephemerals has a positive impact on the overhead, reduces the overhead by 3.68 on average, and the average overhead is 1.89 across all sampling rates. This makes a finalization profiler a practical alternative to estimated object lifetimes. So if you like this presentation of our paper, you can find more information in the paper. For first, you will find all the research questions that will be detailed, and also you have the evaluation, the methodology. We also detail results and implementation details. But this was my presentation. Also, as a conclusion, we can say that finalization profilers can be weakly actionable, and they can have low overhead. Also, that pretenoid in the ephemerals and sampling have a significantly effect on reducing the overhead. And finally, sampling provides relevant object lifetime information. My name is Sebastián Jordán Jordan Montaño, and I will be happy to answer your questions, if any.
Thank you, Sebastian. So do you have some questions for Sebastian? We have a moment for a question.
Hi, Sebastian. Sarah here. I have a question about sampling. So is it sampling of the allocations? Is it sampling of the deallocations or both? I think I missed this part.
Yeah, it is sampling of the allocation. For example, in the 0.1 sampling rate, that means that we are only going to take one allocation per 1,000.
And when we say 100% sampling, this means this is the most accurate measurement?
So, yeah, 100% sampling rate, that it means that we are going to capture all object allocations.
Yes, it's not susceptible to any delays from the runtime. Because at the beginning you mentioned that sometimes when we measure, we can be impacted by delays because of the runtime. So with 100%, we shouldn't expect any delays, correct?
So I will go back to this. So yes, you're right. If we capture all the object allocations, that it can introduce overhead, and it can potentially increase this delta. We cannot know by advance, but our experiments suggest that 100% sampling rate also produces like precise results, but it has the disadvantage that it can introduce also a lot of overhead.
Okay. Thank you.
Thanks.
I feel like I must have missed something because the pre-tenure, you showed the reduction in overhead from pre-tenuring the ephemerons, but doesn't that directly mean that we do not trigger those finalizers until later, until major collection? So isn't there a trade-off with the accuracy, but it didn't, is there a trade-off between overhead and precision there, or is it just all a win to pre-tenure ephemerons?
Thanks for the question. It's really good. And no, for the pretenuring of the ephemerons, there is no disadvantage because the ephemeron has a weak reference to the object. So it doesn't change how the object is going to be, when the object is going to be detected by the garbage collector.
Got it. So it doesn't
It's
change
when the
finalizer
garbage
runs.
collector.
Got it.
Sorry?
So it does not change when the finalizer runs. Thanks.
Yeah, exactly. It doesn't change.
Great. Well, thank you very much for that talk. And with that, we conclude the session. So thank you, Sebastian. And we have now it is the next session starts at 11:40. No, wait. Yes. Starts right now. And the next session chair is Sarah.
Hi, everyone. I am Sarah Hamoud. I will be chairing this session. And yeah, we will have two talks about hardware for memory management. Sang-Yeon Lee will give us the first talk, and it will be about supporting trusted VMs with hardware-based remote memory.
Thank you for your introduction. So, hello everyone. I'm Seung-Yo, a PhD student at KAIST. Today I'll be discussing our paper supporting trusted VM with hardware-based secure remote memory. I will go over some background first. With the rise of AI and cloud services, the demand for memory has been increasing. Moreover,
Just a second. Just a second until we lost the display. Zishan? Yeah.
Yeah, let me continue. Moreover, processing in memory, like database or AI inference, is essential for those systems to achieve low latencies. To keep the data in memory, we need a large memory space. Some system may over-provision their memory capacity, which ends up wasting a lot of memories. So disaggregated memory system has emerged to address these challenges. One way to achieve memory disaggregation is by using remote DMA. This reduces memory waste by making use of idle memory from other nodes. So this diagram shows how one node donates memory to another, and the pages are exchanged over the network. In this figure, on the right, the donated memory is shown in green. So in this paper, we call the donating node as a donor and the receiving node the recipient. In such disaggregated system, efficient memory management is crucial to handle highly fluctuating memory demands, especially in cloud scenarios such as a serverless system or spot instances. So there have been a system that uses memory pool for like containers as shown in this figure. There are some recent studies showing that RDMA can allow effective expansion of memory with some optimizations. And security is also a significant concern in memory disaggregation. First, the confidentiality and integrity of pages stored in donor nodes must be protected, especially when the privileged software of the donor node is compromised. So confidentiality is limiting illegal accesses to the data, and integrity is ensuring the data is accurate or not modified. So we must prevent the memory contents from being exposed or being modified by the donor's host. In addition, when a node donates part of its memory, it must be protected from any illegal attempts to access unauthorized regions. As shown in this figure, a process running on the recipient node should not be able to access memory that were not being donated. So protecting the donor from such malicious accesses is crucial for memory disaggregation. And moreover, there is a study that shows the reuse distance of page address may leak information about workloads. So the donor node looks at the addresses and that are accessed by the recipient to calculate the reuse distance of a certain page. In this diagram, you can see a page address is accessed every 3 page accesses. This access pattern can be a gadget for an attack. So we need to keep the access pattern unknown to attackers. To ensure the obliviousness of this memory content, there are some studies such as ORM, which is notably slow. So in this paper, we designed an obfuscator to hide the access patterns. And to address the challenge of fluctuating memory demands in cloud scenarios, we are assuming that the system is using a memory pool. So in these scenarios, coarse-grained memory allocation can lead to a memory fragmentation. So we decided to manage memory in finer granularity, which is a page granularity. To address these security challenges and efficient disaggregation, we proposed TDMM, which is a hardware-based, trusted disaggregated memory system. Since we assume that the hypervisor is a possible attacker, there need to be a way to ensure security of VM contents from it. So there are solutions to prevent attacks from such compromised privileged software, Intel TDX and AMD SEV. they provide hardware-based protection by encrypting the memory contents of VM. So this figure is the overview of Intel TDX. The green box in the figure denotes the VM that is protected by this mechanism. It is called Trusted Domain VM, and TVM for short. By using this technique, we can ensure the security of VMs. So far, we've discussed about the challenges in the disaggregated memory system. Now we will talk about our solutions. Before we get into the details, I'll discuss about our threat model first. So this diagram represents a brief overview of our system. You can see the recipient on the left and the donor on the right. And the recipient node is running a trusted VM on a hypervisor. The user process swap pages to the memory donor through our TDMM engine, TDME in this diagram, which is an implementation of an FPGA. So this diagram represents more detailed version of our system. So the area colored in blue are TCB, stands for Trusted Computing Base, which contains trusted VM and our system TDMM engine. So TVM ensures confidentiality and integrity of VM memory. And also we can put the TDMM engine in TCB because the FPGA can securely load an encrypted bit stream and disable reprogramming so that it prevents modifications by a compromised host. So this diagram shows swap-in process of a page. The user process in the local node, the left yellow box, is trying to swap in a page from a donor memory. The white boxes explain each step of the process, and the red marks indicate the possible attackers in this process. First, I want to mention that TDMM enables the recipient to access donor memory directly using its physical address, because the address translations are in the critical path, so the complex translation layers can cause performance overhead. So the first step is to check the translation table to know where the page is stored in the donor node. Then it sends a request of the page to TDMM engine. Since we are assuming the page is protected by the TVM, it is safe from compromised hypervisor. Then the request is forwarded to donor's engine to check the ownership of the requested page. Here the page is encrypted, so it's also safe from attacks by malicious network, and the donor's engine checks the ownership so that the donor's memory is safe from ownership attack by recipient. By the way, TDMM can store the pages in HBM of TDMM engine onboard. It's the memory on board to leverage the memory space. When the ownership is confirmed, it returns the page with a response, and the page is decrypted by the kernel, the recipient side kernel. And next is swapping out pages from the recipient node, including how it guarantees confidentiality and integrity. The pages swapped out from the recipient TVM will be encrypted by the kernel, so the confidentiality is ensured. Neither the hypervisor or the network cannot see the contents of the encrypted pages, and TVM keeps the information of message authentication code safely, so integrity is ensured. When the request is sent to donor side engine, it updates the ownership table and passes through the memory allocator. Then the obfuscator randomly selects the page location to be stored to hide the access pattern from the donor host. For example, when the page is being write back, TDMM engine invalidates the previous location and stores it to a new location. So we can hide the reuse distance of this page. Finally, it updates the translation table in the recipient guest OS. This shows the actual implementation of TDMM from memory reclamation to delivering request to the engine. TDMM is tightly integrated to the virtual memory system of the Linux kernel by supporting the operations of front swap, which is an interface used to redirect swap operations to other subsystems. So the process goes like this. When a page is requested to be swapped, it is forwarded through front swap, which is denoted as A. And B, QDMA driver sends the request to user logic for processing. And C, the user logic processes the request, and the response is generated by the donor engine and then forwarded to the guest OS. So this is our evaluation setup. There is a recipient guest running on a hypervisor and a donor node, and TDMM engine is implemented on Alveo U50. By the limitation of our hardware, we just assume the process is running on TVM, trusted VM. Since TVM is a hardware-based protection, the overhead will be negligible compared to the regular VM. And this floor plan shows how resources are utilized in the FPGA. This result shows the normalized performance of fast swap and our system. The performance is normalized by the performance when the system uses local memory only. So basically, this graph represents the slowdown when the pages are swapped to remote memories. So we tested fast swap, an existing solution for enhancing RDMA throughput, comparing that with TDMM HBM plane, which means the performance when swapped pages are stored in donor side HBM without encryption. And the DRAM means to store the pages in the donor side DRAM. And the crypt means that the system uses page encryption and so on. So fast swap shows 63% of performance compared to the non-swapped run, and TDMM experienced 5% performance loss compared to the fast swap. We analyzed that the performance overhead from software encryption is mostly hidden by the read-ahead mechanism in the Linux kernel. Please see the paper for more detail. In this experiment, we measure the memory bandwidth of TDMM and compares it with fast swap. The memory bandwidth is measured with a stream benchmark. You can see the memory bandwidth gap between TDMM HBM crypt and TDMM DRAM crypt is negligible, implying that the major bottleneck for the bandwidth is not the memory. Also, bandwidth loss of TDMM DRAM crypt compared to fast swap is 24% in average for all fast memory ratio. The maximum memory bandwidth is reduced for our prototype, so we require further optimizations of data path implementation on the FPGA board. In conclusion, TDMM builds a secure and efficient memory disaggregation with a 5% performance loss compared to fast swap. So thank you for listening, and I'll now take any questions.
Thank you so much. Any questions for Sangyu?
Hi. Nice talk, and I just have a few high-level question. One is, so in this work, you basically assume RDMA-based page granularity remote disaggregated memory.
Yes.
But with rise of new technology such as CXL, which allows you to access remote memory in byte granularity without going through the swapping mechanism.
Yeah.
So the first question is, how would the problem really change? What I'm asking is the same problem will be there even if we replace this mechanism with CXL like byte addressable interconnects? Or if the answer is yes, the second question is whether you can apply your actual solution to that kind of environment as well. So can you comment on these two questions?
Actually, I don't know much details about CXL security, how the security is ensured in CXL interface. But so the CXL doesn't need the translation tables. It just store and loads from the remote memory. So the problem must be changed a lot, but I'm not sure that the challenges will be the same with these challenges.
So one question, one specific issue I can imagine is you encrypt the page, encrypt in the page granularity, right?
Yes.
But if you actually access in cache line granularity, for example, then you probably need to have a lot more, the MAC code, for example, because you need to actually attach this MAC code for every cache line into the page. So would that kind of thing can, in a sense, make your solution not effective in the new setup, things like that? Is that a possibility?
True. Exactly. Yeah. Thank you.
Okay, so that's one question, and then so my understanding is the problem is more or less there because maybe the donor node may still have access to this memory, local memory, but so problem is likely to be there, but the solution may be very different from yours.
Right.
That's my understanding. But Right. Thanks.
Thank you.
Thank you so much. Thank you.
Thank you.
So next we have Akira from University of Tokyo, who is giving us the next talk about a managed system for microcontrollers with NOR flash memory. start displaying. Okay.
これ使ってみますか。
はい、すいません。
Awesome.
ノートが表示される。
どうやるんやろ。じゃあそっちでノートを表示しながら。わかりました。This works, but this doesn't show the presenter's note. So.
表示されてない。Good afternoon. I'm Akira Inoue of the University of Tokyo. I will be talking about managed memory system for microcontrollers with no flash memory. Script languages make IoT development easier because in scripting language, we can use memory-intensive data structures such as vectors and maps. And garbage collection helps us. Scripting languages require a large amount of memory, while IoT devices have small amount of memory. For example, Raspberry Pico has 264 kilobytes of RAM. By the way, large flash memory is available in IoT devices. For example, Raspberry Pi Pico has 2 megabytes of flash memory. So can we use this NOR flash as a secondary storage for virtual memory? The answer is challenging because flash memory is less flexible than SRAM, and that is erasing the entire page is required before overwriting, and the erasing operation is slow. For example, it took 1 microsecond to erase a single page in Raspberry Pi Pico, according to our measurement. Moreover, erasing shortens the lifespan of flash. More specifically about overwriting, changing 0 bit to 1 is impossible without erasing. The erasing operation sets all bits in the page back to 1. In contrast, changing 1 bit to 0 is possible. We will use this characteristic later. We developed the flash-aware virtual memory combined with garbage collection for script languages. The design goal is, of course,
to reduce the number of erasures in flash memory. In our system, garbage collected heap ranges over the flash address space. This means that the addresses in flash memory are used as virtual addresses. Selected page are paged into SRAM. More specifically, writing to a flash page triggers page into SRAM. In contrast, direct read from flash is allowed. When creating a new object, it is created in SRAM. We trigger page out if SRAM is full. We developed 4 novel techniques for this system. First, object-aware paging eviction policy reduces flash erasures by ignoring writes to dead objects. Second, avoiding unnecessary erasures finds the case where we can page out without erasure. Third, we perform moving GC to gather frequently written objects from others to compact working set. Fourth, we perform garbage collection eagerly to reduce page out. In the following pages, I will explain the details. Object-aware page eviction policy is a page eviction policy to select a page to be evicted as a replacement of a paging in page. It evicts the page with the fewest number of writes to live objects. In traditional policy, pages are chosen on the basis of the count of writes to page. The proposing policy counts writes to object only throughout their lifetime. The background idea of the proposing policy is that we want to evict pages that are unlikely to be written. We estimate the future based on the history. However, we know that dead objects will never be written. When paging out, our avoiding unnecessary erasure technique determine whether erasure is necessary or not. In a naive system, we would erasure before page out whenever the page is modified. The proposed technique omits erasure when all objects in the page are not modified since page in. That after paging and its memory is not reused or allocated in a flash area, which is unused since last erasure. In the flash area, all bits are 1 and we can write to such an area. Our system uses moving GC to move frequently written object to the same page in SRAM. Here, orange objects are frequently written and blue objects are infrequently written. It also moves frequently written objects on the flash to the SRAM. And the purpose of gathering frequently written objects is to page out infrequently written pages and use SRAM pages for frequently written objects. In moving GC, mutators require forwarding information to keep track of moved objects. Traditional techniques are forwarding pointer and forwarding table. The forwarding pointer technique replaces moved objects with forwarding pointers, and this is impossible in Flash because we can't overwrite objects in Flash. The forwarding table technique stores forwarding information in a separate table. This is possible if we put the table in SRAM. However, this is very slow because any access, including access to an unmoved object, involves table lookup. Our system uses a forwarding bit, which is a bit in the object header, indicating the object has been moved. When an object is created, the bit is indicated with 1, initialized with 1. It is changed to 0 when the object is moved. The key point is that flipping 1 bit to 0 is possible in Flash without erasure. When accessing an object, the mutator checks the forwarding bit and skips forwarding table lookup if the bit is 1, because the object has not been moved. Our system has an eager garbage collection scheduler to avoid page out as much as possible. Because page out may involve expensive page erasure. More precisely, our system performs garbage collection wherever SRAM becomes full and leave paging out as the last resort. Next, I explain the experiment to answer 2 questions. The first question is the proposed system better than other in terms of the number of erasure and overhead? For this question, we compared our system with a naive system, which does not have moving GC and uses a traditional virtual memory, and a system without moving GC, which has a proposed virtual memory but does not have moving GC. And the second question is each of our proposed methods effective? For this question, we conducted an ablation study. For this experiment, we implemented the proposed system in MRuby and ran it on Raspberry Pi Pico. And this chart shows the number of erasures, and the x-axis is the number of pages available in SRAM, ranging from 3 pages to 8 pages. And y-axis is the number of erasures, and the lower is the beta. And the blue bar are for the proposed system, and the red bars are for naive system, and the green bar are for the system without moving GC. And the result fell into 2 groups. And this page shows the result for the representative benchmarks of both groups. For delta blue, erasures were reduced by much by our proposal. They were reduced to less than 15% when 3 pages were available in Flash in SRAM. If we compare the blue and green bars, we can see that garbage collection contributed to erase reduction. For DHT11, erasures were reduced by much by our proposal, but garbage collection did not contribute to erase reduction. For the execution time, the results also fell into 2 groups. In these charts, the y-axis is the execution time, and the lower the beta. Again, this page shows the result for the representative benchmarks of both groups. For delta blue, our system was 4 times faster when 3 pages were available in SRAM, and moving GC contributed to speed up. For DH11, our system was faster than the naive system, but if we use moving GC, it slowed down due to the overhead. Remember that the erasures weren't reduced for DH11 by moving GC. For aberration study, we turned off individual techniques. The left chart shows the erasure count normalized to the fully featured proposed system. The right chart shows the erasure time normalized to the fully featured proposed system. In this chart, the lower the better. Therefore, the larger bar indicates the turn-off technique was effective. As shown in the chart, object-aware paging policy was very effective. Avoiding unnecessary erasure and eager GC were effective by a little. For the forwarding bit, it was effective to reduce overhead. It can reduce erasures in principle. I will introduce the related works. SynGC moves frequently written objects to same storages like ours. Their method uses pointer coloring to determine if an object has moved. In contrast, our system uses forwarding bit. CCFLRU is a page eviction algorithm for NAND flash. Their approach monitors objects on a page level. Our approach is object level. And this is the summary. We proposed a memory management system. MLB virtual machine with proposed system successfully executed programs that can't be executed by normal MLB. And our technique reduces the number of erasures by an average of 90% and is 4 times faster. Thank you.
Thank you. Thank you, Akira. I'm afraid we're a bit behind our schedule. Is there any very quick question? Well, if not, then thank you again, Akira. Thanks again. All right, thanks everyone. I think this is time for lunch now.
Yes, time for lunch. We're gonna have an afternoon session starting at 1:40. So please come back for the second keynote in the afternoon session. Enjoy your lunch. All right. So let's start our afternoon session. And the first session of the afternoon is the keynote. Actually, this year, as Hannes said, so we're going to also encourage participation from the other related fields, computer architecture and systems. And the second keynote actually reflects this philosophy, so that we actually invited an expert in the architecture community. And the second speaker is, the second keynote speaker is Dr. Uichul Lim, who is the research fellow and the leader of Solutions Advanced Technology Team and SK Hynix. So Dr. Lim received bachelor's and master's degree from Yonsei University in South Korea, and also he got his PhD degree from Sungkyunkwan University. And before joining SK Hynix, he was an SoC architect, designing like multiple generations of application processors, powering like mobile devices. And then he moved to SK Hynix, and then he's recently focusing on processing in memory technology, which is really fascinating, interesting technology, to especially with emphasis on accelerating large language models. So his research focuses on how we can reduce the cost of developing and serving LLMs, large language models, and generative AI in general. And then he's going to share his insight and then what the LLMs and AI workload is like, and also where we are headed with the development of this generative AI. So let's welcome Dr. Lim.
Okay. Thank you. Thank you for a nice introduction. Okay. Hello, everyone. I'm Uichul Lim, in charge of the processing memory architecture and CXL memory controller project in SK Hynix. First of all, I'd like to thank you very much for inviting me to give this kind of keynote on computing and memory architecture and systems at this ISMM 24. Actually, today I'd like to talk about the next generation memory solution as well as HBM, well known as AI memory for AI computing system. Actually, I'll focus more on the combining computing and memory system to provide higher performance and lower power consumption for AI services. Anyway, actually, it's 1:43, which means it's most sleepy time in whole day after lunch. So actually, I'll try to do my best to keep you awake until the end of this talk. Actually, this talk consists of 6 parts. First, I would like to introduce AI service and its algorithm trends and their impact on computer architecture. And I will briefly talk about the HBM, known as AI memory these days. And in the third chapter, we are going to cover the ChatGPT service, which has renewed at the horizon of AI services and AI model, and the limitation of the GPU computing architecture for that service. After that, I will introduce that most energy efficient LLM accelerator solution using AIM, which is that SK Hynix's first processing memory device. And as you will see later, those kind of AIM solution can overcome the performance and power issues of current AI computing system. In the next chapter, I will give an example of a general AI service and explain the whole kind of entire data pipeline. And lastly, I will introduce various specialty memory solutions, such as a CXL memory-based computational memory solution and the system architecture that I consider to be the ultimate goal. So let's get started. Before talking about the computing system architecture for AI, then we must first understand the trends of AI services and algorithms that become the workload for AI computing. So as a representative AI services, there are recommendation and natural language processing and vision processing system, as you will know. The recommendation system is composed of MLP and embedding that maps products or users in the real world to the deep learning world. And vision processing is built with around that CNN algorithm. Maybe you're most familiar with that. And for the natural language processing, the existing RNN and LSTM-based algorithm has been replaced with that transformer series now. So, yes, there were various algorithms for each services, as you see. But now, transformer algorithm is becoming mainstream model in all AI services. So I will introduce it again later, but in the end, I think the AI model direction will be the combination of that, just the embedding and the transformer, as shown in the picture on the right. So then now let's take a quick look at then why transformer has become a mainstream model in terms of algorithm and architectures. So as you know, then transformer became known through a paper titled "Attention is all you need," published by the Google in 2017. So transformer model ensures accuracy by leveraging self-attention to capture complex data dependencies, enabling precise learning of relationships on input sequences for superior performance in natural language processing tasks. And in architecture-wise, it's highly parallel architecture processes input elements simultaneously, so accelerating training on GPUs and enhancing scalabilities for efficient handling of those kind of large data sets. So to summarize briefly, transformer can provide higher accuracy by attention mechanism and can also provide higher performance and higher hardware utilization by maximum parallelism. That's why transformer became a superstar in AI model now. So then is AI service possible with just a transformer? In order for the AI model to work, then it is necessary to translate the real space data into the vector data that the transformer algorithm can understand. For example, when performing natural language processing, then words should be mapped. When performing the vision processing, then image pixel information should be translated. And in case of recommendation service, then product item and user information should be mapped to the deep learning space. So this kind of mapping operation is called embedding. So embedding requires a large capacity of memory to store the whole kind of mapping relation table and a high memory bandwidth to access the table as fast as possible. Therefore, embedding is a typical memory intensive function, Then after data in real space is transformed into the deep learning space through that kind of embedding, then a transformer model operates with this kind of transformed data. And as we'll be talk about later, transformer-based models vary depending on their size, whether they are computing bound or memory bound. Actually, the representative AI model with a higher proportion of embedding is that the recommendation service. On the other hand, both natural language processing or vision processing feature generally have a large proportion of a transformer model. So if you remember those kind of things, then it will be very helpful in understanding the appropriate workload for each memory-based solution, which will be introduced in the later chapter. So then now everyone will agree that the mainstream AI algorithm is that the transformer model. And one more trend we need to know is that rather than requiring different models for various services, then just one massive model performs various services with a high quality and various types of data, as like this. In addition, I'd like to discuss the trend of AI service level and AI model size. So as you can see the graph on the right, crazy large size transformer series models are emerging recently. So the model size is increasing exponentially, as you see. So as the model size grows to a certain extent, then it is possible to service various tasks that were not previously expected. So a good example would be ChatGPT, which was announced in end of 2022 and opened a new chapter for AI services. And the transformer-based larger model requires a higher performance computer and larger memory capacity. Fortunately, the transformer generative model such as GPT series has a high ratio of memory intake function, so it can be a good opportunity for a memory company like us. Then now I'd like to look at the researches related to the kind of power consumption caused by the movement of data. In terms of energy cost, we can see then how much energy is wasted by just the data movement on the left side on this slide. Looking at the result of 4 typical Google apps, you can see that more than 60% of the power consumption is simply spent on data movement. And the graph on the right is a kind of roof-line graph of bandwidth and performance based on AI model characteristics. As you may know, then x-axis of a roof-line graph is that operational intensity, which is the ratio of the operation on the memory traffic. So as you can see, comparing with just a conventional workload, AI workload has very low operational intensity, which means overall performance largely depends on that memory bandwidth, not the process performance. Of course, there are lots of efforts to get higher computing element utilization by increasing number of batch and manipulating the processing algorithm. So applications, but still have a very lower operational intensity than conventional applications. So in order to, the low operational intensity the application has, then the more power consumed by data movement. So we need to make it, make some kind of solution for those kind of application like AI services. As far as now, I introduced that AI model trends and reason why then transformer algorithm has become the center of AI model. And from now on, I'd like to talk about that just a high bandwidth memory, HBM, one of the most important components in the GPU system for AI processing now. Now, as you all know, then AI work require much larger memory capacity and higher memory bandwidth compared to other existing programs. And the GPU plus HBM system is more optimal than current previous CPU system for processing AI programs, such as the transformer-based model that are processed in maximum parallelism and require a large amount of data than conventional programs. So in particular, demand for HBM is rapidly increasing with that GPU boom following transformer algorithm which can utilize GPU well enough. And this is a brief introduction of a HBM solution. Actually, I briefly introduced HBM technology in terms of capacity, bandwidth, and power consumption. To increase that the memory capacity, per unit area. Then HBM memory comes in a stack of the memory dies that are vertically interconnected using TSV through silicon via technology. As can be seen from the name of the HBM itself, it provides exceptionally higher bandwidth compared to traditional memory technology. So this high bandwidth is achieved by using a wide interface up to 1,000 bits in a kind of HBM2 series. So, and HBM is designed to be more power efficient than conventional memory. So vertical stacking of memory dies reduce that the distance that signals need to travel. So which helps to reduce the power consumption as well. So, and silicon interposer, you know that silicon interposer technology reduce that power for data movement between the HBM and GPU or CPU, like that. And this slide shows that the history and footprint of SK Hynix's HBM. I'm not sure you know that, but SK Hynix was the first to develop that HBM in 2014. After successful developing HBM for the first time in the world, and we are leading that HBM market and ecosystem through the continuous generation development. Actually, with each generation, we continue to increase HBM memory capacity and memory bandwidth while simultaneously reducing the energy consumption, which is very challenging task. Now, then, I'm going to briefly explain then each challenging requirement for the next generation HBM. First, we need to increase that memory capacity of HBM. One approach is to increase that just the number of memory die stack within a single HBM package. This requires advancements in TSV technologies, which allow for vertical stacking of memory dies, and additionally, improvements in the manufacturing process are necessary to enable the stacking of more memory dies within maintaining reliability and performance. And another avenue for increasing HBM memory capacity is to enhance the density of individual memory die. So overall advancements in packaging technology and TSV technology and memory die density are key for increasing the memory capacity of HBM. Second requirement is to just increase that memory bandwidth. So one way to boost memory bandwidth is to increase that just the width of the memory interface, number of pin. So this involves using wide buses to transport data between memory and GPU, allowing for more data to be transmitted simultaneously. And wide bus needs advancements in TSV technology as well. And enhancement in I/O speed can improve the data transfer rate as well. But you know, it may increase the power supply voltage and thus increasing the energy consumption, which we do not want. So anyway, this kind of increasing memory bandwidth is most difficult problem to solve in next generation HBM. And last requirement is to get higher energy efficiency. So in order to maintaining existing power while delivering a higher performance, then power improvement is required through the adoption of a logic process in HBM base die. So by introducing those kind of latest logic process to the HBM base die, we expect that power will be severely improved. Okay. Then do you think that if we use GPU and this kind of HBM solution explained so far, then will there be no problem with all AI services? I'm not sure. So to find out, let's discuss that ChatGPT service itself first. Actually, in general, for a new product to succeed in a real market, then it must possess all three of innovative technology and a stable investment and a wow factor. So AI chatbot such as ChatGPT is based on an innovative technology called, the large language model. And there is a strong investor and driving force such as hyperscalers like Microsoft. And many people are enthusiastic about the AI chatbot service now. So that's why AI chatbot is jumping over the chasm of moving from the early market dominated by early adopters to the mainstream market now. However, problem seems to exist with considerably higher operating cost and substantially longer service latency than previous services. So to resolve this, I'd like to propose a kind of AI-based accelerator system which can provide shorter service latency with a lower operating cost than the latest GPU system. Before presenting the solution, then I will explain the operation of AI chatbot inference and specifically which part has problems accelerating with the current GPU system. As shown in the figure, AI chatbot consists of a prompt stage that understands that input and the response stage that generates an answer. So I asked the question to AI chatbot. What are the issues of learning chatbot with GPUs? And he answers that there are several issues including performance, cost, and power, blah, 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 when processing with GPU. So we may talk about his answer later, but here we will focus on just the AI chatbot inference working process itself. So during the prompt stage, then 9 words are processed in parallel. So 9 computing operations are performed just one time model parameter read. In this case, operational intensity, which is the number of operations per data read from the memory, is 9. So this is not the extremely memory intensive function. However, in the response stage, every time a word is generated, in case of 175 billion model, assuming 16-bit precision, then 350 gigabytes of data should be read from the memory every time. Just one computing operation is performed in one memory operation. Yes, in this case, operation intensity is just 1. It is an extremely memory intensive job. So performance depends on memory bandwidth. As you can see, it takes quite a long time to generate an answer. So actually, in this example, I used that just a word simply, but more precisely, basic processing unit of LLM is not the word, but the token. And on average, one token is around 0.75 words. So in this chatbot example, decoder shown 196 words, and its number token will be around 260 something. Then now let's quick calculate the minimum time required to process response stage with the latest GPU system. It's very simple math. Okay, in case of 175 billion model, then 5 GPU-A, in this case, GPU-A means that H100 NVIDIA's. 5 GPU-A cards are required, and each GPU-A card can provide 3 terabytes per second of memory bandwidth, and giving a total of 15 terabytes per second of memory bandwidth. So the processing time per one token is dividing 350 gigabytes by dividing 15 terabytes per second, means that this processing per one token time is around 23 milliseconds. And whole impulse latency will be 6 seconds. So it's very simple math, and compared to existing service like a searching engine, this is very slow. So then why is so slow even when using the latest and expensive GPU system? As you can see on the right roofline graph here, GPU A can provide 990 teraflops of performance. It's very huge computing performance capability. Actually, in case of that training, then since the batch size is large enough, you can fully utilize that GPU performance as shown on this graph. But in the case of response stage, with the operation intensity is 1, then only 3 teraflops, which is 0.3% of the GPU performance, can be utilized. So GPU is not efficient at processing just memory-intensive workloads, such as AI chatbot response stage. So you are paying high price of GPU, but only using 0.3% of performance, and thus wasting GPU power consumption. Of course, in order to better utilize that GPU performance, I know that there is lots of effort to increase the batch size during the LLM inference. However, you know that this is not an easy task, so as it affects the service latency directly. Therefore, there is a kind of need to create a higher performing and more cost-effective computing infrastructure than a current GPU plus HBM system. So then now I will introduce SK Hynix unique LLM inference acceleration solution now. Then why PIM? PIM means that processing in memory. I'd like to explain then why processing in memory technology can be an optimal large language model-based LLM inference accelerator. The figure on the left shows that the proportion of memory-intensive processing time increases as that AI model size increases. So as you can see that in the bot model, the proportion of memory intensive function is only 5%. But changing to the LLM such as GPT-2, it increases to 45%. And as the model size continues to increase, in the case of 175 billion model, it goes up to 92%. So the overall performance largely depends on just the memory bandwidth of the system. And one more interesting is that actually the memory intensive function we are talking about here is just one function, GEMV, matrix and vector multiplication. And the picture on the right shows that the concept of PIM, processing memory. PIM can utilize that the higher memory bandwidth inside the memory by operating processing unit on each memory bank in parallel. In addition, since only the result of a processing is just transmitted between XPU and memory, the data transmission between the XPU and memory is much reduced, improving energy efficiency as well. Actually, in our PIM device called AIM, we put a processing unit specialized in just the GEMV calculation, which is the most used in AI algorithm, as you can see the graph on the left. So due to those kind of reasons, we believe that the AIM-based solution is suitable for LLM processing by providing a higher memory bandwidth with less energy consumption. And please allow me to introduce then SK Hynix first PIM silicon product, AIM, which is GDDR6 memory-based PIM. Actually, from the beginning, AIM was created with a focus on just the GEMV operation, which is the most basic function of an AI model. So each AIM chip can provide 1 gigabyte of memory capacity and 0.5 terabyte per second of memory bandwidth, which is very huge when performing GenV operation. And AIM support PF16 format precision. As shown on the upper left figure, each of the 16 banks has a MAC unit, so it can provide 16 times the bandwidth compared to the external bandwidth. So theoretically, its performance is up to 1 terabyte per second of memory bandwidth. However, since memory reading and GenV operation constantly alternate, so the available bandwidth during GenV operation is around 0.5 terabyte per second. Next, as shown on the right, I'd like to define then key performance metric for LLM based AI services. Performance per memory capacity, TFLOPS per gigabyte, and also since the operation intensity is 1 in a LLM response stage, it can be rewritten as just a memory bandwidth per memory capacity, terabyte per second per gigabyte. So if there is a target per token processing time, then it can be expressed as a reciprocal of a critical metric. So as can be seen on the graph on the left, right, and AIM can provide much shorter token processing time than the GPU-A. And actually, here I want to tell you one interesting story. Actually, we originally developed the AIM targeting for RNN and LSTM, which was very old one. At the time, the GenV portion was about 90% or more. However, after our development of AIM and as the transformer became the mainstream, the GenV portion fell below 10%, which was very disappointing. In other words, AIM specialized GenV function became useless in transformer, like a bird or something like that. Fortunately, with the release of GPT-2, the GenV portion rose to above 40%. However, even at the time, no matter how fast our AIM processed GenV, the overall performance improvement could not be doubled because there is still 60% processing time that AIM cannot improve. So at the time, I asked my team members to find out which function would be good to add to AIM so that AIM could handle at least 60% of our processing time for LLM or something like that. However, after a few months, the team members came to the conclusion that AIM could handle around 90% of the total functions. So I was surprised and asked what they did. So they said that nothing was done and that it happened because just the model size increased. Actually, this is because that the layer that requires GenV grows squarely, while the other layers grows linearly. So therefore, as the model size increases in the future, then the improvement effect due to the AIM will increase as well, which is very good for us. And now I'd like to explain then how to deploy our AIM in the existing system. Perhaps even if you understand the benefit of AIM for LLM inference, maybe you may be hesitant to deploy it because you might think that in order to utilize AIM, then you need to modify the existing CPU or GPU and also change that software structure on top of it. However, as you can be seen in a previous chapter, as the LLM model size increases, then GenV operation takes up most of LLM processing so that AIM can alone accelerate LLM service without GPU or NPU or any kind of accelerator. So instead of replacing the memory in the existing accelerator with AIM, we suggest making on just the AIM accelerator card and plugging it into the AI server. Just a moment, please. Sorry. So actually, we call an AIM-based LLM accelerator card as just an AMAX card. So in this case, there is no need to modify the existing CPU, GPU, or accelerator, and software modification can be minimized. However, for the AMAX card, it is necessary to develop on this kind of AIM control hub that connects that server and AIM through that PCI and controls the AIM chips. And as will be explained later, we have already implemented those kind of reference design of this AIM control hub chip in FPGA. And this slide shows our AMAX architecture philosophy. As shown in the figure on the right, the AMAX card consists of an AIM control hub chip that receives job from the server and drive each AIM chips, and on AIM chips that stores just whole model data and processes GenV function very efficiently. And as you can see on the left, LLM consists of a GenV function, which occupies most of the processing time, and various other functions, which occupies a very small portion. And so AIM chip focus on processing just a fixed GenV function very efficiently, while the other various functions are performed by just the AIM control hub. So in this way, AMAX card can kill two birds with just one stone, efficiency and flexibility. So it can accelerate various LLM models with higher performance and low energy consumption. So as you can see, most currently known LLM all have similar architecture. In addition, the fully connected layer and multi-head attention layer shown in red account for the majority. So I believe our AMAX system can accelerate most LLM services. And here are the benefits of the AMAX for LLM service. AMAX can provide around 13 times performance than latest GPU system, and energy consumption is reduced to 17% of a GPU system. So in terms of inference latency, GPU-A system's processing time is around, as you see there, 6 seconds. But however, AMAX can provide around 200 terabyte per second of memory bandwidth for GenV function and can answer in less than 0.5 seconds. So if you have some real-time LLM application services, then it can be the best solution. And here, assuming that each AMAX card is equipped with just the 16 AIM chips, it can provide 16 gigabyte of memory capacity and 8 terabyte per second of memory bandwidth. In terms of energy consumption, first, GPU is replaced with just a small AIM control hub, and GenV is processed by a dedicated MAC unit inside the AIM, so reducing energy consumption. And second, as the GenV computation is performed inside the AIM, so energy consumption for the off-chip data transmission can be eliminated. Last, as the GenV performance increases, so the processing time is shortened, and the static energy is also reduced accordingly. So in the end, the GenV operation is possible with only 17% energy consumption compared to the current GPU processing. So you can reduce huge amount of operating cost by using AIM system. And I think that for higher efficiency LLM service, I'd like to suggest that the combination of a GPU system and AMX system. As introduced earlier, LLM service consists of the prompt stage, which is a computing intensive workload, and a response stage, which is an extremely memory intensive workload. So it is more efficient to process the prompt stage in a GPU system and process the response stage in our AMX system. So in addition, usually ChatGPT type applications have a great portion of the response stage, but depending on the application, there are some kind of cases where the proportion of prompt stage is greater. So if the prompt stage system and response stage systems are configured separately, then you can configure the appropriate number of accelerator cards and servers according to your own application. So you can further increase that operating efficiency with that this kind of disaggregated system using AMX card and GPU system. So actually, we developed that prototype of this kind of AMX card introduced so far. So constructed that the AMX reference system is like this, and ported that the LLM model and Q&A application on top of it. And as shown in the picture on the left, the AMX card is equipped with that 2 AIM control hub chip with that FPGA and 16 AIM chips, providing 16 gigabytes of memory capacity per card. Also, as commented before, for higher hardware utilization, the AMX reference system is composed of a GPU card for prompt stage and AMX proto card for the response stage. So actually, currently, the 13 billion OPT model and Q&A application are ported to this kind of system and showcased in a AI Hardware Summit and OSP Global Summit and SC23 in last year. And as you know, 16 gigabyte of memory capacity is not sufficient to run 13 billion LLM models, so we are using 2 AMN cards in this showcase with some kind of parallelism. More importantly, each card is not limited to just 16 gigabyte. It's just a reference system. So, but additionally, AM chip can be mounted to one card for larger memory capacity and higher performance. And so far, I have only focused on just the AI model processing itself. However, for actual AI services, you need to look at the entire AI service pipeline system. So, actually, you know that various services that combines big data and AI technology are rapidly increasing. So in this slide, I'll briefly introduce that, just an example, Graph Driver service as an example to understand the entire data pipeline. So Graph Driver is that one of the widely used ride-sharing service, and it stores real-time data and analyzes it at the same time and sends a live report to the user in real time. And it also analyzes the kind of long-term stored data in order to give more information to the user and sends a weekly or monthly report. So through this kind of service, driver user can decide whether to grab a drive call in real time and predict his or her income or expenses in advance. In addition, by adding this kind of AI model to this data, so more personalized and localized service can be provided. Therefore, the basis of this service can be set to AI model and data analytics. this kind of two stage. So as a general summary again, the entire data pipeline for AI service can be divided into kind of a data collection and data analytics and data use as shown in this kind of figure. So among them, the third step to drive insight from the actual data is that the AI model. And the process of collecting data and analyzing that collected data and performing some kind of processing to pass them onto the AI model is collectively called just data analytics. Actually, from the next chapter, I will cover more various memory and computing fusion solution for data analytics and AI model other than just AIM solution. Actually, this is the last chapter. It's almost over. Actually, you know that nowadays hot keyword, one of the hot keyword is that CXL. So before introducing the next memory solution, I'd like to first explain the new interconnect, CXL. As everyone knows, then computer systems have developed from single core to multi-core and from homogeneous multi-core to heterogeneous computing. And heterogeneous computing system using CPU and GPU or various accelerators together are already widely deployed. And recently, this kind of a CXL, Compute Express Link interconnect has emerged to support efficient connection between various heterogeneous accelerators, including GPUs and central CPU. Briefly, CXL can be viewed as an interconnect with a cache coherent and memory access protocol added to the current PCI interconnects that originally connected the CPU and accelerators. So CXL is composed of CXL.io, which is the basic protocol for PCI device support, and CXL.cache to support cache coherence, and CXL.mem protocol for memory access. The CXL.mem protocol was originally for the CPU to use the memory of the accelerator. By removing the accelerator and leaving just only the memory, then CXL can be used purely for the memory expansion. That we call CXL memory. So unlike that the existing DIMM memory, the memory connected by the CXL can be handshaked with the CPU. So it is possible to add various additional features such as the kind of DRAM cache or data processing core or CXL memory. So therefore, this kind of advent of the AI application introduced the previous slide and the advent of this kind of CXL interconnect, there are more opportunities to apply combination of computing and memory solution to the actual system by using CXL. And now we introduced that CXL-based computing plus memory solution. And internally, we call it as just a CMS, computational memory solution, while we call die-level fusion as on just AIM, accelerated memory. So as in the figure, it is the form of a memory card connected to the host by the CXL, and computing core is mounted as well. So when the host accesses the CXL memory, bandwidth provided by CXL can become a performance bottleneck. However, just by using those kind of computing core in the CXL card, then you can fully utilize that bandwidth that each memory device can provide. So the CXL bottleneck can be overcome and performance improvement can be obtained with that kind of a core. So in addition, by offloading this kind of memory intensive function to the computing core, then data movement between the server and CXL memory can be minimized to reduce energy consumption. And I'd like to talk about that. Then, which types of workloads are suitable for AIM, processing memory, or CMS, CXL-based computation memory solution, which have been introduced so far. So, as shown in the picture on the left, AIM has just a small memory area that can be processed by that one processing element. It is memory bank size. So, but it has a large number of processing elements per memory capacity. Accordingly, it is very stable for a processing workload where the data to be processed is densely stored. So workload density is very high, then PIM is very stable for processing those kind of data. On the other hand, in the CMS, the memory area that one processing element handle is very large, and the number of P's per memory capacity is relatively small. So accordingly, CMS can well process workload with sparsely distributed data. So you need to decide which solution is best to use depending on just the workload density. And memory and computing solution, fusion solution is very much available in various forms other than the die-level AIM and card-level CMS introduced so far. For example, you can easily think of a storage-level computational storage device as shown in the figure below here. Although the basic concept is the same, but its characteristics and the problem to be solved are different each other. As explained in the previous slide, in the case of AIM, which is the die-level fusion, since a computing element operates for each bank in one memory device, the memory capacity per processing node is relatively small. In contrast, in the case of CMS, which is the card-level fusion, then since a computing element can use a number of memory devices, the memory capacity per processing node is relatively larger. Of course, in the case of a storage level, second level, third level, the memory capacity per processing nodes becomes larger. So as we already talked that, this kind of characteristics determine the appropriate workload to execute in each memory plus computing solutions. So we will have those kinds of various computing and memory fusion solutions. Actually, before closing this presentation, I'd like to introduce a new computer system architecture called data hierarchy. The basic concept is that every memory layer has its own processing unit to minimize data movement among entire memory hierarchy vertically. Since every hierarchy layer has not only memory but also processing element as well, so it is not just a memory hierarchy but data hierarchy, we call it. Yes, concept is very simple, but there are lots of challenging questions to be solved to realize those kind of things. So today I'd like to introduce several interesting questions on this architecture. So first question is that then how to place the data at the proper memory layer? Because once we place the data, we don't like to move any kind of data between the layer. So provide the solution for this question, we need to understand the characteristics of the data and processing algorithm that use it. Second question will be, then what is the optimal process architecture for each layer? I think if we focus on specific applications, we can define it. For example, for AI system, then main memory layer process can be optimized to perform just a matrix multiplication, while storage layer processor need to optimize for kind of pre-processing operation like data analytics. And last thing, more complex question is then how to distribute those jobs between, to each data layers processor and how to aggregate that result. Actually, data hierarchy architecture is a kind of more complicated heterogeneous computing system. Not only horizontal workload distribution among heterogeneous computing unit, it also requires that vertical workload distribution and communication among the layers. So we should care both vertical and horizontal job distribution and communication simultaneously. I think this kind of data hierarchy concept is still just a buzzword yet, but I hope that someday we will have a chance to discuss it seriously together. So thank you for listening, and I hope my talk was interesting enough to keep your attention until the end of presentation. Thank you.
Okay, thank you, Dr. Lim. We actually have time for 1 or 2 questions. Anyone want to ask questions? Please, can you come over and use the microphone?
So my main question is about how do you compete with GPUs? So GPUs have 128 or stream processors and so on. And how many processors do you have within your AIM solution next to 1 gigabyte? How does that compare? As you scale memory, does the compute similarly scale with HBM plus GPU together?
Oh, actually, we are just focusing on that GPU cannot do. Actually, there are 2 kinds of functions in LLM. One is just a gem. Gem function is matrix by matrix multiplication, which is GPU can do well. In that case, the performance depends on the processing performance itself. So GPU can do well with a very massive parallelism. But GemV is that matrix by vector multiplication, which is at most memory intensive workload. So the performance does not depends on the processing performance. Yeah, that's why we focus on those kinds of things with just minimum performance unit in the memory banks. Thank you.
All right, next question.
Thank you for that interesting talk. I have a question about the picture of the data hierarchy. I like this picture, but the picture is very complicated. So my question is, how can we program it? How can we use that complicated system? Is there any good abstraction?
Actually, it's that question that I want to ask you all in this community. So actually, that's why in a modern computing system, the most as consumption is that just moving the data. So we need to minimize that moving data. Then how can we do that? How can we place that proper position in that memory hierarchy or something like that? And how can we communicate with each other's processor in a vertically and horizontally? So that's why I ask the question to this kind of software community to solve this kind of problem together. Yeah, that's it.
Thank you for the nice challenge.
Perhaps the good starting point is SK Hynix sponsoring next year's ISMM or PLDI. So that we can find answer together. Okay, any other questions? I think we are about time. So let's thank the keynote speaker again.
So yeah, we will start the next session next. I'm Mike Bond. I'm the general chair. You might have noticed you haven't seen me yet. I was very delayed. Glad to be here with you all. While you're getting set up, I will probably Hannes and Jay didn't say it during the Let's see, the next speaker, please go ahead and get set up. So I really want to thank Hannes and Jay. They did virtually all the work for the conference, along with the program committee. As you may know, the general chair, not a whole lot of duties, because PLDI covers a lot of things. And in this year, the general chair didn't even show up till now, so they also covered this part, the welcome remarks and so forth. But I did manage to make it for chairing this session. That applause, I assume, is for Hannes and Jay.
This works.
Okay, it's working.
Should I move it closer?
I think it should be fine.
Okay.
So the first talk is by Tomer Corey from Technion, an undergrad, I believe, at Technion. Yes. The one-pass compactor. This is the intellectual abstract section.
Okay. Thanks for the introduction. My name is Tomer Corey. I'm a student from the Technion, and today I will be presenting the one-pass compactor. It is joint work together with Professor Erez Petrank. And it is an intellectual abstract as we propose a new algorithm, but we do not accompany it with implementation nor evaluation. So the one-pass compactor is a full heap compaction algorithm. It requires a single heap pass, which is nice because traditionally the complexity of compaction algorithm is measured by the amount of heap passes that are necessary for it. And it is parallelizable, which means that it can be suitable for multi-core platforms. The motivation for this research is pretty clear. Garbage collection is very common in modern environments, and many garbage collection methods cause fragmentation. This fragmentation hurts program performance, first by making the allocation process more difficult or even blocking it when there is enough free space in the heap. And second, by making the usage of for resources such as the cache and virtual memory inefficient. Luckily, we can solve this problem by compaction. So when we think about compaction, there are really two goals. The first and obvious one is to compact the objects in the heap, meaning gathering all live objects together into a contiguous space. But the second one, just as important, is to keep the correctness of the program by updating each pointer to point at the new location of the object it refers to. So it's easy to think that if we have an object that moved, we need to fix the pointer to it, or else it might be catastrophic for the correctness of our program. In this paper, we focus on mark compact, in which compaction is following a marking phase. This approach enjoys low memory overhead, and it preserves object order, which has been proved in practice to be beneficial for program behavior. So a problem that we encounter is that full heap compaction requires high time overhead. And throughout the years, there have been many ways in which we can deal with it. The first one is reducing the complexity of the compaction algorithms. Naturally, if there is less work to do, this work is done faster. Additionally, the compaction can be made incremental, meaning that instead of compacting the whole heap at once, we divide the heap into different segments, and at each point, we only compact a segment. This not only shortens the wait time, but it can also increase throughput, as a segment should only be compacted if it is necessary. Additionally, we can make the compaction parallel, in which case multiple threads will run the compaction algorithm together, thus the overall time will decrease. And the compaction can also be made concurrent, in which case compacting thread runs in parallel with a user application, and there is no wait time, or very little. So all of these approaches are widely covered in literature. This is just a short list. In this work, we focus on, first and foremost, reducing the complexity, and then we also offer a parallel version of the algorithm that we present. So we begin with asking the questions, how many heap passes are necessary for Mark compact? Now, in the worst case, a single pass at least seems unavoidable. Imagine a case in which there is a little bit of free space in the beginning of the heap, and then a lot of objects scattered throughout it. We will need to go into each one of these objects and copy it into the beginning addresses. Previously, in the past, compactors required 3 heap passes. An example for that is the Lisp2 compactor, which in the first heap pass installed forwarding information inside of objects. Then in the second pass, it used this information to fix pointers. And in the third pass, it actually moved the objects. Later, there have been compactors that only required 2. We will delve into some of them later in this presentation. Examples for that is the Yonkers threaded algorithm and IBM's compactor. And eventually came the compressor, which only required 1.x heap passes. With 1.x meaning 1 pass over the whole heap, and then another pass, which is a pre-processing traversal of an auxiliary data structure, which is smaller than the heap, but proportional to it in size. And a follow-up question that we ask is, can 1 pass be reached? And as the name of this paper might hint, we answer with yes. In this paper, we present the 1-pass compactor. It is the first compaction algorithm to only require a single pass. And later, we extend it and offer a parallel version of it. So during this presentation, we will begin by reviewing existing algorithms that serve as the building blocks of the 1-pass compactor. We will go through the threaded algorithm of Yonkers and through the address mapping approach showcased in IBM's compactor by Abu Ayad. We will then notice beneficial properties of this algorithm, and we will combine them together to create the 1-pass compactor. And we will finish by discussing a little bit about the parallel extension, since we do not have time to cover the whole thing. So in the threaded algorithm, the idea is to take pointers to an object and transform them into a linked list beginning in that object's header. Then when this object is handled and a new address for it is computed, we can traverse this linked list and fix all pointers in it. It can be done in a smart way, which does not require extra space and instead uses existing fields. So a short example of this process is if we have, say, objects A and B, which contain a pointer to object C. When we reach object A, we notice the pointer in it, and we add it to the threaded list going from C. Then we do the same to object B when we reach it, and we reach a state in which all objects are threaded into, all pointers to C are threaded into a linked list beginning in its header. Then when we reach object C and we calculate a new address for it, we can traverse this list and update the pointers in it to reach the final state in which the pointers are fixed. So we make a distinction between 2 kinds of pointer based in the direction in space to which they point. If a pointer comes from a higher address to a lower one, we call it a backwards pointer. And symmetrically, if it goes from a lower address to a higher one, we call it a forwards pointer. And we will use this definition to notice beneficial properties. So an observation that Yonkers makes is that when the heap is traversed sequentially, and whenever a pointer is reached, it is threaded to the object it points to, then when we reach an object, all forwards pointers to it have already been threaded, which means that we can use this threading mechanism to fix all forwards pointers during the first heap pass. This observation helps Yonkers create his algorithm that requires only 2 heap passes. In the first pass, we traverse objects by order, and whenever we reach an object, we start by updating all pointers in its incoming pointers threaded list. Then we thread all pointers outgoing from it. And then in the second pass, whenever we reach an object, we update again all the pointers that have been added to his threaded list since the previous pass, and we move the object. It's important to notice that this is a sequential algorithm, and not only it is sequential, it is notoriously hard to make parallel, as it really builds on the order in which the traversal is done. The second building block of the compactor is IBM's, of the one-pass compactor, is IBM's compactor by Abu Ayad. This compactor uses an auxiliary address mapping, which is kept in a compressed way to not require too large of memory overhead. And we basically can think of it in the following way. It gives us the functionality to give it as an input the old address of an object and get as an output its new address. This can be used to compact the heap in two passes. In the first pass, whenever we reach an object, we move it to its new location, and then we calculate and record its mapping in the auxiliary map. And then during the second pass, we fix every pointer we reached based on this address mapping. So we make this following observation that so far has been overlooked. If we have a sequential heap traversal, and whenever we reach an object, we record its old to new address mapping, it means that every object, whenever we reach an object, we already have this address mapping for every object before it. And this can be useful because we can use mapping to fix backwards pointers on the first heap pass. So a corollary of these two observations is that we can combine these methods and fix all pointers in the first heap pass, since we have a mechanism to fix forwards pointers and a mechanism to fix backwards ones. And this leads us to the one-pass compactor in its sequential form. The algorithm is quite simple. What we need to do is to traverse the heap in order, and then for every object we reach, we start by calculating its old to new address mapping and record it. Then we update all pointers that have been threaded to it. We move it to its new location. And for each pointer in it, based on the direction into which this pointer points, we fix it with the relevant method, which is either threading for a forwards pointer or address mapping for backwards pointer. So this algorithm only requires a single heap pass, and it incurs the same space overhead as Abu Ayad's compactor, as it uses the same mapping mechanism. And we will now see a short example of it. We have objects A, B, and C, blue, red, and green, respectively. We begin by reaching object A and calculating and recording its old to new mapping. Then, since there are no pointers threaded to it yet, we move it to its new location, and we fix pointers in it based on the relevant method, in which case it's a forwards pointer, so we thread it to the pointed object. Then we reach object B. Again, we record its old to new mapping. It does not have any pointers threaded to it, so we move it to its new location, and we fix the pointers in it based on the relevant approach, in which case, since it is a backwards pointer, we fix it using the address mapping. Last, we reach object C. Again, record its old to new mapping. And in this time, we do have pointers threaded to it. So we traverse the threaded list and fix these pointers. And then we move it to its new location and again fix pointers in it. This time, again, a backwards pointer, so it is fixed with mapping. And this was it for the sequential algorithm. In the sequential case, objects are traversed by their order in the heap, which helps us have certain guarantees about them. We know that based on the direction that a pointer points to in space, what is the useful way to fix it. But when we want to think of the parallel case, which is important since many modern systems have multiple cores, if not all of them, we cannot rely on these spatial considerations anymore. So we need to employ a paradigm shift. And instead, we want to think about temporal properties. Basically, we would like to replace the spatial notions of forwards and backwards with the temporal notions of not yet and already. We would like to simplistically say that we will use threading to fix pointers to objects not yet visited and use mapping to fix pointers to objects already visited. Sadly, life is not simple. When we have a parallel compaction algorithm running on multiple threads, objects can be visited concurrently, and different threads advance in different speeds, so we need to take all that into account. As you all know, the devil is in the details, and we will not have time in this presentation to focus on everything we do to make the algorithm parallel. So instead, we will discuss a few key points of this parallelization journey. First of all, as mentioned, we have this paradigm shift of making the consideration temporal instead of spatial. Then we take the critical section of the threading operation and we make it contain only a single compare and swap instruction. We have to make sure that when a pointer is threaded to an object, it will actually be fixed when that object is handled. We need to make sure that when we move objects, we do not break any linked list, as this can hurt the correctness of the program. If not careful, we can run into an ABA problem, so we have to avoid that as well. And not only we need to keep the program correct, we also need to do so in a manner that will allow us to compact in high quality and achieve satisfying load balancing between the threads running the compaction algorithm. So to conclude, in this paper, we present the one-pass compactor. It is the first compaction algorithm to achieve heap compaction using only a single heap pass. And it achieves that by combining beneficial properties of existing algorithms. And eventually, we also provide a parallel version for that algorithm. So thank you for listening. If you have any questions.
Thank you. This was a great talk. Do you have plans to implement it?
I'm not sure yet. I'm still doing my undergraduate studies, so obviously I did not have time so far. Hopefully in the future.
Maybe I can convince you in errors to implement it in V8, because I think this could be really useful in the browser context.
Okay.
We'll talk later.
Other questions? It's sort of a related question, which was, so this has the best asymptotic performance, but do you have a sense for like what would be your guess for what algorithm would perform best?
So this is a great question, as we know that the threading operation in the general case can be less efficient than the address mapping approach due to cache behavior. We like to think about this measure of pointer locality, which will measure the average distance that a pointer points to. And our hypothesis is that if a program exhibits a high pointer locality, then the threading method will be more efficient, and it could be very competitive to, say, the compressor.
So the risk of showing my ignorance, I'm not in this area, but so is it necessary to move every object in the heap? Because if the heap, let's say the object takes, say, 4 kilobytes, and I'm allocating things in terms of 4 kilobytes, why should I move it?
Oh, so again, great
So
question.
it looks like you could be doing less than one pass.
Yeah, that's a good question. Again, this is a theoretical work, and in many systems that are actually implemented, big objects are not moved.
Thanks a lot.
Thank you.
So the second talk in the session will be about Batchit, and will be given by Matthew Parkinson.
Thank you. So this is about optimizing message passing allocators that produce consumer workloads. So I'm going to unpack the title because it's quite technical and go through each of the items in there. So I'm one of the authors of SNMalloc, which is an allocator some people use, and this is basically some exploration we had in trying to optimize that, thinking about some way in which we could optimize that, which also happened to apply to vmalloc, and this is kind of what we did in that space. So to start with, I'm going to talk about produce consumer workloads. So what do I mean by that in terms of sort of memory management? So here's kind of your... Sorry. Okay, so I hear myself now. Sorry. So what I'm going to talk about is produce consumer workloads. So what do I mean by that? So here's a sort of a simple program where you might have, say, 4 threads. There's one thread being your network ingress, so it's reading from a network, generating work, flowing it through a system. There's a couple of workers that are dealing with the work, and then there's one thread that's putting the work out. So if you think of this from a memory management point of view, your ingress thread allocates some buffer, passes it off to some worker. The worker's going to do some work, possibly generate a response. Some more work comes in on the ingress thread, that gets sent off to another worker. That generates a response. The responses go to the egress thread. All of them are sort of, everything's flowing right, and then things start getting deallocated. But what you see is that as you go through this, kind of the blue things are allocated on one thread and deallocated on a different thread. And the yellow things are allocated on one thread and deallocated on another thread. And the orange things are basically what you can end up with is sort of a very asymmetric shape in terms of where something's allocated and where it's deallocated. And often these things are of different sizes, so there isn't kind of a nice affinity to sort of, I can't reuse a response object necessarily as a request object because they might be of different sizes. So you get a flow one way for the application, and the deallocation has to flow in the other direction. So that's what I mean by produce consumer workloads. This is sort of something that you do find in production systems. So what I'm going to focus on next is message passing allocator. So by this, I'm sort of talking about the design of SNMalloc, the design of memalloc, and actually TBB-malloc. TBB, Intel's allocator, also has this sort of shape. But before I can kind of go on to that, I want to give you a bit of background on sort of the design of allocators. So for those of you who aren't sort of on the malloc and free side of the fence, this might be helpful. So to start with, in this I'm going to call a single allocation an object, just because that's sort of how I talk, and I can't change that. Size class is an approximation of the size of an object, so we'll just group objects by size classes rather than precise sizes. And I'm going to say slab for a region of memory that contains objects of only a particular size class. Many allocators use a different word. In fact, I'm not sure I found any allocator that uses the same word as another allocator consistently across all the terms. So hopefully this is helpful. So in the beginning, for the design of an allocator, you had a thread, and it was asking for memory. And there would be some kind of data structure indexing the memory, saying what's available, and then there's sort of the chunks of memory. And these could be kind of interleaved in a bit of ways, but basically that's it. There's some indexing structure and some memory. And when you introduce threads, oh, my slide's advanced on its own, you end up with a lock basically protecting the structure. And this is a great point of contention because everyone has to access this every time they're allocating and freeing. So that's not great. So then you get sort of a different design that came out, the one I first came across like this is JE-malloc. Horde is similar, but basically you have effectively an allocator per thread. And each of those still has a lock associated to it, so there's some kind of lock to index, so when you're accessing that data structure, but you should have low contention because you're accessing your own allocator, so as long as you're not doing anything like a producer-consumer workload, this would be fine. But if you've got anything where you have allocations and deallocations needing to flow between threads, it's not great. So when you get sort of like TC-malloc style, so this is where you have thread caching, so you have one allocator with a lock on it, but then you have some layer of caching on top of it. So in TC malloc, what might happen is, so for this produce consumer workload, we allocate something from our thread cache. It gets passed across to the other thread. It puts it into its thread cache, but its thread cache is full. So then it goes and grabs the lock and puts it back into the main allocator. Now, depending on how your thread caches are set up, they might go back in individuals, but probably in batches. So it reduces the contention on the lock, but you still have this sort of flowing around the system. And then, obviously, you've emptied your thread cache, so you have to grab the lock to get it back. So in this, you can get some bad behavior. And a project I did quite a few years ago, we were using JE malloc, and we had this producer-consumer style workload, and we kept hitting lock contention because we were batch allocating and batch freeing stuff. And we were just permanently emptying thread caches and basically causing contention. And that was kind of where the design of SM malloc came from, and there's a sort of similar thing in the design of me malloc. But you want sort of to do some kind of something that doesn't involve locks. So the design of me malloc, sorry, is Dan here yet? He's not here yet, so I can say it and not worry. He is coming to PLDI, but not this talk, thankfully. So in me malloc, effectively, for every slab of memory, there's a queue. So when you want to free memory, you put it in a sort of, there's basically a message queue per slab of memory. So if we take our producer-consumer workload, what happens is we allocate some piece of memory from our heap, we pass it off to another thread, and then it sends a message. So it doesn't actually touch the allocator, it just sort of adds it to the queue. So there's a message queue, and then that gets put in there. So this means you're not grabbing locks, you've got sort of lots of queues as well, so there's one per slab. So the likelihood of contention can be quite low, and you're not having to actually do the work of sort of consolidating, working out how many things there are, etc. You're just putting it in a queue, so it's quite a lightweight operation. And, oh, I've missed one animation. Okay, so SN malloc is kind of similar, but very different in many regards. So in me malloc, there was one queue per slab. So one, or actually it's a stack in me malloc. There's one messaging structure per slab. Whereas in SN malloc, there's one messaging structure per allocator. So every allocator has basically a receive queue and a send queue. So these are all of the allocations, so the send queue are all of the allocations which deallocations we need to do to another thread, but we're going to batch them up and send them across in a while. So in this case, when we do kind of state and produce consumer example, gets sent to another thread, goes into its send, comes in, it goes, oh, this is a not for me, so I'm not going to deal with it directly. And occasionally it checks its receive queue, so it might go, oh, I've got some memory, I better put that back. And then it puts it in its send queue, and then every so often it will send all of those in one batch back to the originating allocator. And there's a bit of a sort of data structure for working out how to do that in kind of batches between different threads, which is in the original SM malloc paper. So that's kind of allocators as I know them. So the final part of the title was optimizing. So to optimize, you have to think of something that's wrong. So in me malloc, there's really good cache locality when you're doing this because you're sending messages to a slab. So all of the messages are kind of for the same piece of memory, very close together. But every time you send a message, you're doing, in me malloc, it's a cache loop because it's a stack. So you're doing a serializing operation for every remote free. So every one of these producer-consumer frees. So that's killing your instruction level parallelism. And if you've got contention, it's even worse because you've got a cache loop. So if you happen to be freeing to the same thing from many threads, potentially you've got a lot of things hitting there. So that could be quite bad. And you can sort of create benchmarks that show that for me malloc. SM malloc, on the other end, doesn't have this issue with the atomic sends because it does all of its batching. It does big batches. It sends them across between threads. It sort of distributes the work. So SM malloc practically does almost no interlocked instructions compared to the amount of allocations and deallocations it does. But it has poor cache locality because everything it gets can be interleaved with other things, so it has to go and read this queue of messages, and they're all over the place. So that then means that, like, when I was
when I've been staring at traces of SM_malloc, I'll see loads of cache misses on this thing that's supposed to be my nice fast thing, which is not great. So now I can introduce the final bit, batch it. So this is basically adding some batching infrastructure into both me_malloc and SM_malloc to improve the performance. So in me_malloc, what we're going to have is a little cache, basically, of recently freed things. Now, unlike thread caching, we're not going to reuse them. We're just going to keep them there and then send them in groups back to the originating slab. So this is a slab-indexed associative cache. So I think the one in the paper was 16-way 2 associativities, but it might have been 1 associative. 16-way 1 associative, I think. But we tried quite a lot of different things. So when you get a deallocation in, you put it in the cache. If the cache has some things in it already, if you get contention, just send them across. It's okay. That was what you're going to do anyway in me_malloc. It just happens that if you're doing a lot of stuff to the same slab, you'll send maybe 4 or 5 or 10 deallocations in one go. And that's going to really reduce your contention in the contended cases. Oops. Yeah, so it was that. So in me_malloc, we're doing exactly the same thing. Sorry, in SM_malloc, we're doing exactly the same thing as me_malloc. We have a cache now. But what we're going to do is build up these little chunks to go back again. And when we produce our send queue, we're going to make them actually slightly more complicated. So they're going to be, instead of going all over the place, we'll build cyclic lists of the things we're sending back. So we have a list of cyclic lists. So when we send it across, we can process each little cyclic list in one go. And again, that'll have good cache locality. And so basically we get better cache locality as we're going through. And the thing that Wes did that was really nice was he also managed in 16 bytes to store 2 pointers and the length of the list. Because obviously you want to keep the length of the list. So then you could add it without even looking at the list, which reduced cache costs even more. So we ran some benchmarking. We did the me_malloc bench. I'm just going to present a micro benchmark that Wes built that was really nice. So this is kind of like a straight producer-consumer, so there's no intermediate workers, just one producer, one consumer. So what we sort of found with me_malloc was that it starts out with a little bit of improvement, and then as you get more ways in which things are going, that's kind of where the contention started to hit in the micro benchmark. So you're getting lots of kind of cost from that contention, so we get to win, and then it starts creeping back this way, which is as you get more and more ways, the likelihood of the cache actually working goes down. So you sort of have this improvement as contention rises, and then reduction as the cache efficiency falls off. Whereas in SM_malloc, it behaves very differently. So SM_malloc, it basically works really well with the most likelihood of a cache succeeding, because we weren't facing any contention issues in SM_malloc. It was all about the cache miss rate. So the better the cache works, the better it works in SM_malloc. So it's a slightly different performance characteristic while being effectively the same optimization. So there's further details in the paper. So for me_malloc benchmark results, and both me_malloc and SM_malloc have some hardening features, and that also leads to quite a lot of complexity in how you actually implement some of these features when you keep the hardening switched on. So there's graphs and diagrams, and an optimization to me_malloc and SM_malloc.
Questions?
Nice talk. Great insights. Just wondering, did you get a chance to look at any bigger workloads? I can see the value in the micro benchmarks in this case, but just wondering if you had any other.
I haven't yet, so that's one of the reasons why we submitted as an intellectual abstract. But we had an idea, and we'd see how to put it into things, but I need to talk more with Dan to get into memalloc and look at some benchmarks there. But the use cases for smmalloc at the moment, I'm not sure would exercise this. So
yeah. Okay. So then the pivot would be, do you have any thoughts on what will happen when you do that? I mean, based on what motivated the work in the beginning?
Sorry, I'm not sure.
Based on what motivated you to go down this path, how do you think this will, can you speculate on how this might perform in the sort of situations you really wanted to work on, as opposed to the...
Yeah, so I think in the real situations we'll have to spend a lot more time looking at cache sizes and associativities and like actually tuning that, because so for a micro benchmark I can find a micro benchmark that hits whatever cache size I want and whatever associativity I want. It's actually finding the right workloads to then stress and get a sort of a good thing, but we've not done that work.
Thanks.
Other questions?
The next speaker doesn't mind having an extra 5 minutes.
I'm trying to pressure the explicit memory management people to ask a question rather than me try to come up with something intelligent. It's not working. Yeah, sort of related to that. Do you think that there are potential cases where it won't perform well that you need to be concerned about?
So for smmalloc, I think it should always be better because it's just doing a little bit of pre-processing. For memalloc, it's going to hold open slabs of memory for longer, so it can potentially introduce fragmentation. In the benchmarking we looked at, it didn't, because it's quite a small cache. But then the efficiency of the cache might be a problem. So if we make the cache big enough, then we'll hold open more slabs, which then causes more fragmentation. So that's kind of the downside we could see. And with any of these, some of the micro benchmarks in the paper, if it's too small an example, then anything you do to the code change can lead to strange behaviors in terms of performance. Ryan?
This may be kind of a basic misunderstanding of this area, but it seems like both of these strategies, all the strategies you described today, implicitly treat it as the best we can do is to get that freed memory chunk back to the original allocator. But it's a bit frustrating, isn't it? Because you've just touched that memory most recently on the receiver, and you mentioned that there are often differences in size classes that mean that the receiver cannot reuse the memory directly. So do we just kind of give up on that efficiency at the outset and assume the best you can do is get the memory back to the sender? If there are differences in size classes, couldn't we reallocate these chunks or recognize these differences to somehow adapt to this pattern to be able to keep the memory moving forward instead of going back?
Yeah, so when you're doing a size class-based slab allocator, so whenever you're doing a size class-based allocator, it's very hard to change the size of anything because you've sort of committed to that in advance, and there's sort of all your metadata is structured around that, so that becomes a challenge. In the case where it's sort of a similar size, then like the TC malloc strategy actually works quite well because your thread cache, you can sort of bounce it around nicely in that sense, but even if you've got one thread that's only ever doing deallocation because it's the egress thing, it's just getting stuff in and sending it out and then deallocating, that thread will almost never do any allocation. Right. So you do get some scenarios like this. So I think memalloc's probably the most widely deployed allocator in this sort of shape, and it does seem to perform very well in comparison to TC malloc and stuff, even in the cases where you're keeping stuff, even cases that work well for thread caching.
Interesting. So even in an extreme case where we have like 10 or 20 processing stages that are all moving data forward along them, in theory it sounds like there'd be a case where you would just switch over to TC malloc, and that might do better at enabling receivers to reuse memory and pass it forward. But in practice, you're saying people just use memalloc for these examples, and it seems to work better in practice.
I think it depends what company they work for, what they use.
Thank you.
Thank you. I now get your joke about the next speaker having an extra 5 minutes. So Matthew will now talk about reference counting deeply immutable data structures with cycles.
If I can get there. Oh, where's it? No. Okay, thank you. Thank you. So this talks about reference counting deeply immutable data structures with cycles. So this talk is very similar in style to the previous talk. So I'm going to start by unpacking this deeply technical title. So what do I mean by immutable data structures? So immutable data structures, so here you've got your sort of applications of persistent data structures, functional languages, or like concurrency, where you might want to share things between threads and you don't, each thread can be accessing it at the same time, and if there's no mutation, everything gets much easier. So your shared data is much easier if everything's immutable. And then there's sort of, in the immutable data structure world, there's sometimes things are just constructed immutably. So you might have everything's immutable from the start, sort of you just allocate it and everything you know what it is. Or you might have some operation that turns it immutable at some point in the future. So some languages have something like freeze, sort of this object graph will no longer move, change at all. And that can be sort of at the level of an individual object, or it can be deeply immutable data structures. So that, I mean that, I'm going to have to hold this, I think. That means that everything you can reach is immutable. So you could have some object graph. This object graph has some objects in it. So if A, oh no, if A is deeply immutable, then it means everything it can reach is going to be immutable. So reference counting. So in this audience, hopefully everyone knows what reference counting is. You keep the in degree of an object. Here's that same graph. It's got some numbers on it. If we take away a pointer, a number goes down, the object goes away, more numbers go down, but the objects go away, and everything gets collected. So reference counting, awesome, love it. Reference counting with cycles. So life gets a bit harder. Let's add a few more edges. And now reference counts go up a little bit. And now if we want to collect this, oh, it doesn't work. So reference counting with cycles, classic problem. Everyone hopefully knows that. So in this talk, I'm going to talk about reference counting deeply immutable data structures with cycles. So the research question is, if we have deeply immutable data structures, can we make reference counting collect those data structures even in the presence of cycles? So the observation is that if we have deeply immutable data structures, then the cycles do not change. So we might be able to afford to do a slightly more expensive operation up front. And for those of you who remember sort of your undergraduate data structures and algorithms, strongly connected components are a nice way of factoring an arbitrary graph into an equivalence relation and a DAG. So what I mean is that every graph can be turned into a DAG, so something that can be reference counted nicely, and an equivalence relation. So basically you've got little groups of objects. So that means if we do reference counting at the level of SCCs, then it's safe to reference count an arbitrary graph. So here we've got that same picture. Now this has two strongly connected components. It has B, which is a strongly connected component with a single object, and A, C, D, E, which is a strongly connected component of 4 objects, because they could all reach each other. So in the paper, we present an algorithm, which I'm going to fly through in the time I have, which is basically, if you go to Wikipedia and read the path-based strongly connected component algorithms page, and then squint and think a bit about changing it so it does reference counting at the same time and fiddle a bit, so it uses union find rather than a slightly different data structure, you will get the rest of the paper. But what we do, basically, we're going to use union find in the algorithm. So this audience perhaps isn't as aware of union find as like the theorem proving people, but it's a good way of representing equivalence classes. So you keep two operations around. One is tell me the representative is equivalence class, so it gives you something you compare for equality. So you can ask two objects are in the same equivalence class, find their representative, ask if it's the same thing. If it is, then they're the same. And union, which basically allows you to merge two equivalence classes. So like the common algorithm for this is parent pointing trees. If we do basically our path-based union, path-based strongly connected components at the same time, we can generate reference counts as we go. And in the algorithm that I'm going to present on the next few slides, we're going to have a single field inside an object that represents the reference count, or that this is something we haven't visited yet, so unmarked, or a rank. And rank is a sort of technical thing from union find, so you have to do merging in a certain way. So it's keeping track of how large a strongly connected component you have. So the code fits on a slide, possibly not legibly, but on a slide. So we have a stack of tentative strongly connected components. So the algorithm sets up basically pending, which are all of the things we think could be strongly connected components that we've visited so far. And then every time round, we're going to basically call this freeze on an element, and it's basically a depth-first search. So we're going to look up the status of that particular object, which is this, like either it's a rank or it's a reference count. A strongly connected component we've already found. It's got a reference count, or it's unmarked and we haven't visited it yet. So the first sort of case analysis of this is, so we look at the status and we see that it's unmarked, in which case this is our main DFS exploration of the graph. And then there's a pre-order step where we say, well, this is a new thing, so I'm going to make it its own strongly connected component and mark it sort of tentatively as a strongly connected component and put it in this set of, in this stack of them. And then I will look at all of its fields recursively, actual algorithm, not recursive. And then we do a post-order step, so on the way back out, we have to then say, okay, if we're still the top of the stack, then we can take ourselves off and we can say this is a completed strongly connected component. And then we get, if it's a completed one, it has a reference count of 1 because there's one entry into it. And then later on, we might add some more, which is what's going on, sorry. Yeah, if we find, so, which is what's going on the bottom part is when we find a back edge, a forwards edge. And then these, if we reach something on the stack of pending things, then we're going to pop back up because that's basically a back edge that we've determined through the path-based exploration. So that was perhaps a little abstract, so I have a pretty graph. This is also in the paper. It took up a whole page. So if you don't follow it here, you can follow it there or not. So we look at A. The depth first order is going to be alphabetical. So A goes to B, and it sees B. It goes, so what's going to happen here is it finds B. It has no children, so it doesn't have to do any work. And then it's going to see that it is still the top of pending, because pending is A and B. So that creates a strongly connected component with reference count 1. And that was very quick. So then we look at C, and we push C onto the pending stack. So we've got A and C. Then we go push D in, and we push D onto the pending stack. So we've got A, C, D. And then that sees B. So B now has an edge coming in, and that lands here. So that's, we found something that already has a reference count. So we've already found it, so we give it an extra count. And then we pop back out. So as we, sorry, which way did I go? So we followed the edge from D to C now. So C is on our pending stack. So that means we've created a back edge because we're looking at something we've already seen. So we'll merge those and we'll remove D from the pending stack. And then we pop back out. Sorry, pop back out, but we're still in a pending state, so we've still got edges to look at. So we go to E. And then E sees that it's pointing to something that's on the pending stack A. So it unions those, and then it goes through this while loop here, popping back up until it finds the right thing. So it unions those, and then a bit more time, and the algorithm finishes, and it puts a reference count of 1 on this. So that gives us our basic calculation. You can probably find someone on Wikipedia, on like YouTube or something, doing a much better job of explaining path-based strongly connected components, but that's my attempt. So then we want to release something. We can say
we can create edges to intermediate points, like we can point at B here, and now that has a reference count of 3, so we could have more indexes in, and we could drop the reference on A, and now this whole thing has to go away in one go, so that kind of needs to disappear, and what we really have to do is follow all of the edges to stay within the SCC before we follow edges that come out of the SCC. So we have to kind of effectively do a depth-first search where we prioritize internal to external edges. So we implemented this. The algorithm is almost linear time. We're using union find, so that gives us a very, very slightly off linear time thing, but it's inverse Ackermann, so not very much. The performance, so what have we got? So here we've got running the code basically, so we've got alloc. So if we're building, in this case it's 5 minutes, cool. Doubly linked list. So the blue line is for various sizes, how much it costs to allocate that with SNMalloc, see previous talk. And then we've got freezing cost, so this is the cost of going through that data structure and actually running this path-based strongly connected components on it. So you can see it's a bit more of an allocation. We also, in the runtime that we built, had a mark and sweep collector. So you can see that that's the orange line here. So it's a bit higher than that as well. But most of the examples we looked at, it was within double to 2.5 sort of cost. So freezing was about twice to 2.5 times the cost of actually doing a straightforward mark phase where it didn't collect anything. So just doing a depth-first search over that graph, which it's quite similar in cost. As you might notice, things get slower as you get faster. So I was a bit worried about this because I was trying to present a paper on an almost linear time algorithm, and it got worse as it got bigger. So I was trying to work out why that was, and eventually I decided that machines have caches, and caches don't hold bigger workloads. So everything gets slower as you get bigger, and you can't show a graph that looks linear. So then I added these extra lines at the bottom, which are the number of steps followed by the find algorithm, which is linear, and it's perfectly linear. So the algorithm is linear, just machines aren't. In the paper, you can look at more graphs that all look pretty similar in terms of various different data structures with different levels of cyclicities and back edges, forwards edges. I think one of the interesting things is depending on the order of the fields can affect the cost, because sometimes, like with a doubly linked list, which one is it? This one is much worse than this one because it's following one of them's following the forwards edges first, and one of them's following the backwards edges first. And if you follow the backwards edges first, everything stays nice and compact. And if you follow the forwards edges first, it doubles the size of some of the stacks that you have to keep track of. Cool. So applications of this. So we were looking at this because we wanted to use it for shared immutable state. So in the Pony programming language, there's basically a way of freezing memory and then allowing you to share it between threads. But in there, they're using tracing GC, quite a challenging sort of thing that works across actors to do that. But you have to manage that memory like managing it in a classic way. And we wanted to see if we could do something better. So sort of as part of this project I'm working on for memory management, we wanted to build this for that. So that's kind of where this came from. For functional languages, this could be quite interesting to replace some of the tracing GC stuff. In fact, Brian's talk earlier when he was talking about the reference counting for the big old stuff and it not working well for cycles, I was like, ooh, I want to talk about that. So that might be interesting. We're currently prototyping this. We're sort of looking at Python and seeing if we could add something to Python because there's interesting reference counting going on. So if we added immutable state to Python, could we do this algorithm there? And then reviewer D, it wasn't B this time, asked, could we apply this to tracing GCs? And I think that's a really interesting question, which I don't have a good answer to. But to go back to the original question, if we restrict to deeply immutable data structures, can we make reference counting collect those data structures even in the presence of cycles? The answer is yes.
That was very interesting. And I agree with your enthusiasm for reference counting, of course. But there was something I missed, so I don't quite get what's happening here. So if we look at the picture you've got on the screen, just for example, the deeply immutable, that also refers to the references, or no?
So the topology is deeply immutable, but the reference counts can mutate. So you can create references into it.
Into it, from outside?
From outside, but you can't change anything it can reach.
Ah, okay. So then what I didn't get is that the algorithm you described sounded to be essentially a trace.
Yeah.
In which case, why not do a trace?
So because
the outside references are changing.
Because the outside references are changing.
That's the key. That's the key thing I was missing. So the internal references are not changing, but the outside ones are, and then you want to know which ones you can kill when the outside references change.
Exactly. Yeah. So it's when can I collect this stuff? So like if you have long-lived data structures that are deeply immutable, tracing so in principle, right, with this sort of squinting, sort of seeing 2.5x, right? If you have to trace it more than a couple of times, then this would be a win.
Yeah.
Because you don't know when it goes away until that.
That was the next thing I was going to ask or suggest, is that green line there is a one-time cost, whereas the other ones are...
Precisely, yeah.
Okay,
other than the fact that when you introduce reference counting, then you've got reference counting manipulations, whereas with tracing you don't have those, so there's slightly more subtlety there. But
sure.
You're very aware of that.
Other questions? So the I guess have you thought about using this for like a general purpose language that has lots of mutation like Java? What that would look like in terms of speculations and speculations?
So after our reviews and thinking about our rebuttal, we did. So one thing I thought would be an interesting sort of design point is if you have sort of a generational kind of scheme. So your early generations you still do with as you would, but when you promote things to one of the sort of longer lived generations, you might apply this to then basically say, well, I'll use reference counting for those older generations, and then periodically you'd have to do something to recalculate so it's always safe to use an incorrect strongly connected component graph, right? So if you connect things which aren't actually connected, it's safe, but you won't collect memory. So potentially there's memory that could be collected, but you won't. So, but that's kind of a generational hypothesis, right? You stop looking at old stuff because, wow, it's probably not going away now, is it? So this might be a way of getting some of that older stuff away quicker if there are cycles involved, or yeah. So that would be sort of my starting point, but I don't really have time to do it, but if anyone's interested in talking about it, I'm happy to.
I wonder also if this would be useful in the context of Rust, because there's a lot of type information about immutability, and then also Rust has a reference counting cycle collection problem that it doesn't guarantee collection of cycles. So I wonder.
Yeah, I haven't. The code's written in C++, but it could equally be written in Rust to do this. So yeah, I don't know if the immutability in Rust is deep, so in that sense, it wouldn't apply in the sort of way in which at least it's presented in the paper. But I think one of the reasons why we wanted to write an intellectual abstract on this is because we thought it was an interesting trick, and people might apply it in another way. So.
Time for one last question. Actually, it's time for the break. So I think we'll come back in 20 minutes at the hour, right? Thank you.
a huge monster. 2 days a week, so it feels like I'm mostly learning new stuff. Yeah, it's good.
So I'm very pleased to be able to be here to chair this. The first talk will be a remote talk online. I think it's a recorded talk, but there is an expectation that there will be live question and answer afterwards. So hopefully the technology is with us, and we can start with the recorded talk, which is called SSRD, Shapes and Summaries for Race Detection in Concurrent Data Structures. And the authors are Shalfan Sun and Rajiv Gupta from UC Riverside, and I believe the speaker will be Shalfan Sun, but let's see.
Hello everyone, thank you for joining us today. I'm Xiaofan from UC Riverside. Today, I will be discussing shapes and summaries for race detection in concurrent data structures. Firstly, let's talk about concurrent data structures. Those are data structures that can grow and shrink as needed. Most are node-based. They are used to synchronize state in parallel applications. They can be excised and changed simultaneously. Here are some common ones used in parallel applications. Skip list, replace a priority queue or a map. Linked list, used for concurrent queues. AVL tree, used for maps and union sites. Implementing those data structures correctly is tough due to concurrency bugs, especially data trees. So we want a technique to help us automatically find bugs in multi-threaded programs. One powerful method is concolic testing. Comparing to random test, concolic testing uses symbolic inputs and a solver to solve the constraints to excise their path, which gives a more reliable result. Here's a quick review of how it works. First, user needs to specify some symbolic inputs as the selector will select the path pi, and the execution of path pi on S gives a symbolic constraint ci. The constraints are collected from branch conditions along the path pi. Then the constraints ci are sent to the solver when we need a concrete value to run some functions, or we need to reduce execution complexity. It will solve the concrete input I for symbolic input S and send to the executor. Finally, the bugs are reported if it has, and it moves to the next iteration to test path pi plus 1 using random or the first order until all user expected passes are tested. Then I should bring up an important concept: data shape in pointer-based data structure. It consists of pointers and the memory objects they point to. While we care about data shape, we first meet the problem that one data structure shape cannot cover all paths. Let's consider a case where we want to expose more paths in programs with concurrent data structures. For example, we assume S is a global object, global variable. In thread 0, there are two reads that happen in two paths with thread 1, both right reads. However, if we see the condition of those two paths, one requires nike pointer equals to null and another null. So we have to use two different shapes to expose the reads. Only one shape can only expose reads 1 or reads 2. You can never expose both using one single shape. Manually find those shapes are hard, error-prone, and tedious. We wish to automatically generate shapes to excise different paths. Now, let's discuss the performance issue. We want our system to explore the shapes efficiently, but there is redundant work if a function is called it multiple times. For example, if there are m paths from the main function to foo is called m times, generating m shapes. Each call inside foo needs shape generation 2, let's say producing n shapes. So we ended up with m times n shapes, leading to a lot of redundant work. Can we explore the shapes just once for each pass in full? Consider this example with function full and min. In the min function, node n and user input argc are symbolic. For pass A, we assume it will call from the min function and take the true branch. The left figure shows the final shape for pass A after calling full. The second figure shows the date shape in another pass B. You can find there are lots of similarities in the generated shape because we call the same function. The shape growth in full is independent to the main function. If we can find the part that shape generated in the function full and make a summary for shape, we can greatly reduce the redundant work in shape exploration for next time calling the same function. Okay, let's do the next summary construction. To create a function summary, we run the full function before starting test. We call this step public unit testing. In unit testing, the parameter A passed in is a symbolic pointer. The data shape will expand when pointer is dereferenced and related constraints are collected. In this figure, we show what the shape infer for path 1 looks like. The shape will expand when date field is dereferenced in node A next pointer. So the node N0 is created and date equals to 0 has been set there. Then if we have a branch in the function, we need to generate different shapes for those paths. We will use a decision tree model to select which shape to use. So the condition is collected during unit testing. For example, A arrow next not equals to now in this example. This is a key idea how to summarize a function and make the generated shape can be reused in the future. However, decision tree cannot be too deep. So if there are loops or complicated control flow graph, only the top levels could be summarized. Other parts will fall back to the original function call. If there are function calls, like adding a function bar here and call this function, we can isolate the side effects that function bar are made, assuming no global variable size. Only the date shapes passed in and the return value are affected. So we reset the shape to symbolic pointer with unknown and create the symbolic value as B for the return value B. Following branch must be resolved again due to those side effects. Even its previous condition A next or not equals to none or true, but you could see we still need to evaluate both of those cases because we didn't know the side effect. After introducing the construction of the summary, let's have a look at this example to see how the summary is getting invoked if we give a summary of function full and an input shape. Let's use this example in path A taken. Path A is taken in the main function. Okay, so we have to follow the decision tree model. First, we evaluate the branch decision from the root node of decision tree and quickly reproduce for both branches. For the true branch, we meet a function call for the bar, and we will receive call summary invocation method for function bar here to produce a result shape. If it's summarized, or if it's not, then we just simply run it. Assume it will return to variable b and I change number 0 to 1. in the data field of the last node in this shape, like this is highlighted shows. The modified shapes will be used for the following steps and map back to the pointers in the summary. Here we map back the shapes and use the return shapes in the following step. And this branch condition should be evaluated again using the returned shapes and producing the final result. Now we know the branch should take true and corresponding changes to the shape presented. After we really made those changes to memory, all side effects in the function full are reproduced. The data shape should be returned to color. This is how we invoke a summary. To make the system can detect data traces effectively, we desire a two-stage solution. Concurrent unit testing is running before the testing to run each function individually and produce the summaries and use a log-side approach to detect potential risks. Then in the concurrent testing of full program stage, we will start testing from main function and confirm each risk is really happening and use the summary to speed up it. We can compare the normal function call with summary invocation. First, both of them should evaluate the branch conditions, but then once we need to generate the data shape, inside the normal function call, we have to collect pointer constraints. We have to call solver to solve the shape and handle all memory access. Doing some invocation, we skip those work and directly get the generated shape from memory, which is the cached result, copy the memory object, and the shape is generated and suitable for current stress rate. This is much faster than keep generating shapes for function call. In addition, only non-local memories access have to be handled since all local memory size is already reflected to the memory object in the data shape. Next, let's talk about experiments. To evaluate the effectiveness of risk detection of SSRD, we made a few benchmarks by eliminating synchronization operations from open source programs, including skip list, enrolled linked list, priority queue, and AVL tree. We compare our approach SSRD with a baseline approach, Cloud9, which is the one we built on top of it. This is a symbolic execution engine, supports multi-threading. Give each program an initialized data structure and used to run the test case for Cloud9, but we will ask SSRD, our approach, to automatically generate data shapes to test them. In this figure, we can see the deep blue shows the number of risks detected in each benchmark using SSRD. Comparing to the light blue Cloud9 one, almost all benchmarks is getting out. However, this is due to the ability that's exploring data shapes. You will find much more paths are taken. If you see the yellow line and the orange line, the yellow line shows the number of paths explored using SSRD, which is much more than the orange one, which shows for Cloud9. So the cost is much more slower. However, with the number of paths increasing, it will take much more time to run those test cases. Many complicated programs may take too much time to get a meaningful result. Summarization is a way to reduce the time required. Please see this table. It shows without using summarization, How much time will taken in those test cases, since summarization requires an additional summary construction time? This time is also listed there. Then, if enabled, how much time has been reduced? If we see the first line as an example, it says skip this test case when running insert function without summarization. It takes 326.56 seconds without summarization. But it cost 172.3 plus additional 0.1 seconds for summary construction time. So it becomes much faster. The reduction time have been 47% of the total time. In the parentheses, we list if we didn't consider the construction time, how much time will be reduced, which is 47.2%. In those benchmarks, there is a still case getting worse when enabling summarization. We look into it and find the reason is the decision tree is not deep enough to cover the path. Each function can be described as a control flow graph, but decision tree model is not able to cover very deep path. If that happens, it may hurt performance. Even though there are cases not covered, we could still see in the most cases, summarization contributes a lot for for this system efficiency. It's a high-performance cache mechanism for frequently used paths and quickly reproduce the shapes. It gave us a way to find databases both effective and efficient. Okay, that's all for today. Thanks for listening.
Do we have the technology to bring them on for questions? Are they there? What time is it in California at the moment?
Hi.
Okay. Hello, can you hear us?
Yeah. Good afternoon.
Okay.
This is Shofar
Do
San
we
from
have any questions
California.
in the room? That is the question. Does anyone wish to ask a question? I can hand you the mic. Or we may have gone to all this effort for no reason. I'm not seeing any hands going up. In which case, perhaps we should just applaud so the authors can hear us and thank them for their presentation. Okay, they got up early. So let's just get you plugged in here. While we get set up, I'll introduce the next speaker. This is a paper called A Heuristic for Periodic Memory Allocation with Little Fragmentation to Train Neural Networks. And the speaker will be Zijian Zhu. Zijian Zhu.
Good afternoon, everyone. So my name is Zijian Xu, and today I'm going to talk about our latest work, a heuristic for periodic memory allocation with little fragmentation to train neural networks. So first of all, I'd like to talk the overview of our research. So in today's training of neural networks, it consumes a lot of memory, as talked in today's keynote. And there are a lot of memory optimizations. And when memory allocation is highly optimized, the PyTorch caching allocator, which is used as the default memory allocator in PyTorch, consumes extra 29.5% on average space due to fragmentation. So memory is not fully utilized. So to cope with this problem, we designed a new heuristic for defragmentation in periodic memory allocation, and especially targeting neural network training. And with our, instead of using the online allocation algorithm in the PyTorch allocator, we designed an offline allocator which can utilize the memory more efficient way and just with 0.4% fragmentation. And I'd like to introduce the background first and why memory fragmentation is becoming more severe in training neural networks. So when doing the inference for the neural networks, usually the memory is not a big problem in terms of the memory consumption. Because in the inference graph, the computation graph only consists of the forward path, and the intermediate values between the layers can be freed once the layer is completed. However, in the training, the intermediate value of the forward path are still needed for the backpropagation. So when computing the forward path, we need to store all of the intermediate results, and we have the peak at the beginning of the backpropagation. So memory optimization is very important here for training large models or training models with large batch sizes. And one of the common ways to cope with this problem is called recomputation. And in recomputation, instead of keeping large tensors on memory for a long time, we just discard them and recompute them from smaller inputs when needed. So in this example, instead of keeping the red tensors in the left figure, we rematerialized it as the green values during the backpropagation. So by this optimization, the number of computing nodes is increased, so the computation time takes longer, but the peak memory is decreased. And there are a number of recomputation solvers studied recently, and the recomputation is shown to be very strong optimization. So the top figure denotes the load size against the runtime progress in the training of vision transformer model. So in the forward process, the memory consumption increases, and in the back propagation, it decreases. And the memory consumption is unimodal, and PyTorch caching allocator works very well. It can cache almost all of the allocation and runs without allocation overhead. However, when recomputation is applied, the peak memory is reduced by 90%. However, the resulting allocation pattern becomes much more complex, and the load size fluctuates near the peak, and this complex memory footprint produces fragmentation. So why defragmentation is important? Of course, we cannot fully utilize the resource. And actually, PyTorch caching allocator provides some methods to cope with this problem by managing their cache blocks in an online way. However, when doing this kind of online management, it involves many calls of CUDA malloc or CUDA free during the runtime, and it decreases this training throughput, sometimes even by 50%. So next, I'd like to talk about our approach for defragmentation, and I'm going to state our problem formulation and algorithm. So our approach is offline memory planning. This is because in the training of neural networks, memory allocations have a specific pattern, and the pattern is repeated. So the overall process of the training allocation can be illustrated as like this. So at the first, they have pre-process, like the allocation of weights. And when the training loop starts, they repeat exactly same the allocation patterns, especially when the shapes of the input are fixed. And after the training iteration, it has post-process such as the releases. And usually the bottlenecks are the training iteration. So we focus these training iteration to optimize. So our allocator works like this. In the first iteration, it traces allocations while allowing slow allocation, like Malloc managed. And once we obtain the whole allocation history, then we use the allocation history to compute optimal address assignment for all of the allocations. And from the second iteration, we use the optimized allocation that has almost no fragmentation. So now our problem can be simplified as this. Actually, the problem is called dynamic storage allocation, and it is widely studied in this field. So in the dynamic storage allocation problem, or DSA problem, given allocations, our task is to find the minimum address space range that can fit all of the allocation requests. So this problem can be reinterpreted as a special case of two-dimensional bin packing problem, where each rectangle is allowed only to move vertically. So in this figure, the vertical axis represents the address space, and the horizontal axis is time axis. So each rectangle is allocation. It has fixed starting time and fixed end time, but its address range can be, well, determined by allocator, so it can be moved vertically. And two rectangles must not be overlapped because two allocation must not share the physical storage. To solve the DSA problem, we introduced a new notion called topological ordering, which determines address assignments. So given a topological ordering is an ordering among rectangles. So for example, in the left figure, the topological ordering among rectangles is D, C, A, E, B. And we determine the address assignment such that first we place D to the lowest position, and then place C to the lowest position, then place A, E, B. So topological ordering determines the address assignment. And in the right example, now the topological ordering is A, B, C, D. So we first place A, then place B, place C. So A is placed under D because A has smaller topological ordering than D. So the DSA problem can be rephrased to the problem of finding the best topological ordering among rectangles such that the address space is minimized. So one idea to solve this problem is a naive simulated annealing. So in this naive simulated annealing, we first initialize a topological ordering such as D, C, A, E, B, and in each iteration, we slightly change the topological ordering, like to D, C, A, B, E, and in each step with the new topological ordering, we evaluate the memory assignment, and if the address range size is minimized, then we update the current topological ordering. If it's not minimized, we still probabilistically update the topological ordering to avoid converging to the local minima. However, such naive simulated annealing is slow because it takes order n log n time for the memory evaluation of a single candidate. So I'm going to explain why it takes order n log n. So given a topological ordering, we compute the address assignment for each rectangle in that order. And when when placing a rectangle, the offset, we use a segment tree data structure to manage the maximum address of that time. So when placing a rectangle, the offset can be computed as the maximum address size between the range of the starting time of that rectangle and the end time of that rectangle. And when the rectangle is placed, we have to update the maximum address size as the offset plus the height of the rectangle. So segment tree data structure can handle the range max and the range update queries in order log n time. So when we repeat this n times, it sums up to order n log n time. So what we want to do is to optimize our algorithm for better convergence. And the idea is to reuse computation to evaluate multiple topological ordering. So from this slide, I will use 4 or 5 slides to explain the idea of the optimization. And we are going to show that we can evaluate these n topological orders in order n log n time, which means that we can evaluate a single candidate in order log n time. Yes. One of the important observations we use for the optimization is that the reverse topological ordering gives the same address range size as the original topological ordering. So in the left example, we place D, C, A, B, E in this order, and it's bottom aligned. And the reverse order means E, B, A, C, D. And in the right figure, we place E to the top. So it's written as top aligned. We first place E to the top and place B to the top. Then place A to the top, place C to the top, place D to the top. And these two assignments gives the same address range. And this is the important observation. So this is the original n topological order described in the bottom aligned way. And this is the n topological order described in the top aligned way. And as I explained, for each case, they have the exactly same height, which means the allocation, the use address range size is the same. And this slide is important. And actually, we can mix both bottom aligned and top aligned way. So the allocation before E is bottom aligned, and then we allocate E, and allocation after E is top aligned. So even with this kind of allocation rule, we can get the same height if E is on the critical path, which means the peak load size is achieved at some point during the lifetime of E. So by that rule, where we can compute these the address range size of these n candidates in n log n time, such as follows. So the height can be computed as the maximum height below E, which can be computed using a segment tree, and the height above E can be computed using another segment tree, and the height of E itself. And if E is not in the critical path, then we can simply take the maximum height among all time. And by taking the maximum of these two candidates, we can get the memory address range for all candidates. So by using this optimized simulated annealing, we can evaluate n candidates at the same time, and it enables direct transition to good solution. And I'm going to show some experimental results. So we have collected the memory memory allocation history from the training of famous vision and text models, and the number of allocation is about between 2,000 and 9,000. And we also use 3 comparator algorithms. One is the online algorithm, PyTorch casting allocator, and we use 2 other offline algorithms, best fit and first fit heuristic. So in these offline variants, unlike the online variant, we do not process allocation in the requested order, but in the descending order of their sizes. And in the left figure, the horizontal axis is peak memory consumption divided by peak load size. So this is always greater than 1, greater than or equal to 1. And if it's greater than 1, it means that there is fragmentation. So the colored bars denotes the fragmentation. So when using PyTorch casting allocator, we have a lot of fragmentation. For some mobile net cases, it even have about 50% fragmentation. And by applying our heuristic, we can remove almost all of the fragmentation. And to test our method on a wider range of allocation patterns, we also tested our algorithm on random allocation patterns. And even in the random cases, we observed that our algorithm can nearly completely remove the fragmentation. And we also measure the training throughput. So in the left figure plots the relative training throughput against available GPU memory. So if GPU memory is enough, then the PyTorch casting allocator can cache all of the allocations, and its training throughput is 100%. However, when the GPU available memory becomes more smaller, PyTorch caching allocator will produce the OOM error, even if the peak load size is less than 4 gigabytes. A PyTorch casting allocator offers some configuration to cope with this situation, as I mentioned previously. However, when using that configuration, the training throughput can be degraded to 50%. And by using our offline planning, we can achieve near full memory utilization with maximum throughput. In conclusion, we designed a new heuristic for the DSA problem, and it achieved good performance on the training and even random cases. If you have any questions, I'm happy to answer them.
Any questions? Please come to the mic.
Thank you for the interesting talk. I have actually 2 questions. One is the size of the segment tree. How large is it?
So the size of segment tree is the size of number of allocations. So it's not very large. For example, the number of allocation size is 10,000, then it's the order of the 10,000.
Okay. Another question is that, if I understand correctly, you harvest the allocation pattern in the first iteration and make the optimal allocation strategy
Yes.
Before the second iteration.
Correct.
So, how can you execute the first iteration with a limited size of memory?
Oh, that's a very good question. So in the first iteration, in practice, we can use CUDA-Malloc manage, which can utilize both the GPU and host memory. So even if the allocation does not fit in GPU memory due to fragmentation, it can still allocate in the first iteration. Thank you.
Okay, thank you. We're a bit over time, so I'll halt questions there. Thank you very much. Well, thank you one more time. So this is the last talk of the day. And the title of the talk is ESPN, Memory Efficient Multi-Vector Information Retrieval. And the speaker today will be Narasimha Reddy from Texas A&M.
Howdy. All right, that's a Texas way of saying hello. Okay. This work is done by my student, Sushav Shrestha, who's in a summer internship, so he couldn't make it here today, and with collaboration with Zhang Wang Li, who's at Samsung. Okay. The motivation for this work came from various reasons. Obviously, Samsung produces SSDs, and they're trying to look at how to use SSDs efficiently in machine learning applications. And so part of the work came from there, okay, part of the motivation. So just to give you a brief background, the keynote touched on a lot of these issues here, but information retrieval, for example, you go to Google and type a query, you expect to get the document that's relevant to your query. And the way this is done is through several means, several ideas are done, but now mostly what are called multi-vector neural information retrieval. And the basic idea here is that you have a bunch of documents that you want to index, and you compute something called document embeddings. And the idea is these things are pre-computed, you have them available, and then you type in a query in Google search box, and that query also gets translated into something called a query embedding. And then you look for the similarity of the query embedding and the document embedding, and then you pick up those documents that are close to the query embedding, and whichever has the highest similarity score, you pop them up as the results for the query that you typed in. Okay. And the basic philosophy here is that through natural language processing, and you basically get the gist of documents, what the documents contain, and what the query is asking for, and somehow these embeddings in the space, vector space, relate to each other, and this similarity in the embedding space results in getting good candidates for the search query you have given, okay? And the way this is proceeds is given here in this boxes here. So you type in a query, the query gets encoded, and I'll talk about how this approximate k-nearest search gets done, because you have lots of documents. You can't be searching for all of them, so you need to quickly figure out what are the likely candidates. And then from those candidates, you get the detailed embeddings, you do compute the similarity score, and then you give the documents to this user, okay? Okay, so here is how the approximate neighbor searches works. So when you pre-computed the documents, you compute them into this vector space embedding space. And what happens is all of these embeddings, originally when BERT was created by Google, Google used something called 768 for some reason, vector spaces dimensions. But now these things use up to 4K dimensions. So each of this query, even though I'm showing you here in a planar graph, is actually in 768 or 4,000 dimensions. And what you do is to take all the documents you created for these embeddings, and you create a clustering means. You just do some kind of K clustering. And so what I'm showing you here is in this diagram here, there is a cluster 1 and a cluster 2 and so on and so forth. And you have a central candidate to represent this cluster. Okay, so what you do is you create all these embeddings. And for each of this cluster, you take a centroid or mean element, and then you create that as a way to figure out what this cluster represents. And when a query comes in, what you're trying to do is to look through this cluster candidates and find the first candidates that closely match this query. And what you do is once you have the match of those queried clusters, you go into the clusters and actually find the documents that are necessarily relevant, and then you rank them, and then you bring those documents out to show to whoever is asking for this. Okay. So in order to do all this quickly, typically what information retrievals do is to create something called inverted indexes, and you store these inverted index in memory and try to use them as efficiently as possible. Okay, so just to give you an idea here, so the table here is showing you two sets of approaches to doing the document queries. The traditional way of doing things are in the top level, which you see here, the indexes are roughly less than 2 gigabytes. But with this, I can't move here, okay. With the multi-vector models, you see those indexes sizes are now in several gigabytes per each of these approaches. Okay, BERT version 1, which was created originally by Google, and there are a bunch of optimizations afterwards, but the original one had 154 gigabytes of index for this macro data set, which is up 3.3 gigabytes. Okay, now what you're trying to do is use this in a memory system like this. All of you know how the memory hierarchy works. You have a GPU caching system that has very few memory megabytes. And then if you're using GPUs to use this, GPUs high bandwidth memory is the next to the GPUs. And then you go to system memory, sometimes use the system memory with the CPU memory as a backup for when you're running out of HBM. And then eventually get to secondary storage in order to get things done. Okay. At least when we started looking at this problem, the access that we had for the GPU we had was about 28 gigabytes. And now you can buy, if you have money from NVIDIA, you can buy a GPU that has 80 gigabytes of HBM. But right now, let's assume for the time being, we're limited to 25 gigabytes of HBM. Okay. So if your index has anything more than 25 gigabytes, it's not going to fit in the GPU's high bandwidth memory. And in order for this to be indexed, you'll have to take the help of the system memory. And even with that, let's say system memory is about 128 gigabytes, you're now straddling these index sizes that I showed you are getting to be larger than the memory that's around there. And the idea is, how do you manage this in a system like this, okay? Okay, just to clarify one more thing, is that the way this thing works, let me back up a little bit. The indexing has, as I mentioned, when you do the documents indexing, you do two things. One is you compute something called a CLS index, which basically represents the whole document as one thing. And then you also compute something called bag of word index, which is, again, another representation of the document, but you basically take something similar to a paragraph at a time, and then index the paragraph at a time to represent the document. Okay. So this index that I talked to actually has two components. That's the thing. Okay. All right. So the whole idea is to how do we reduce this? People have looked at various ways of looking at this. Primary thing is to reduce the size of these models. And as you see here, original one had 154 gigabytes. Over time, people have been able to reduce that down to something smaller. And this is by basically reducing the number of bits that you use to represent the dimensions and throwing away what they think is non-essential bag of words, indexes, and so on and so forth. But you lose a little bit of accuracy as a result of doing these things. Okay, so what we wanted to do was, at this time when we were looking at this, was could we move some of this to secondary storage and reduce the pressure on memory and not having to put everything in memory? That was the question we were trying to figure out. And the reason for doing this was that both the GPUs have come up with something called GPU direct storage, which was before, when you wanted to move data from SSDs, you had to first move it to the CPUs, and then only move the data from CPU to the HBM in the GPU. So it actually had to go through this hierarchy. Now with the new GPUs, you can directly move the data from SSDs to HBM to make this a little bit less painful and more efficient. So the idea was could we take advantage of this GDS and move the data from memory to storage and reduce the pressure on memory. That's the motivation for this work. Okay, so far the problem, okay? Okay, so here is just an example. We did this just to give you an idea of what happens. In this example, the index was about 20 gigabytes, and we did here with 30 gigabytes of memory, everything fits in. You get done in 45.6 milliseconds, the query latency. But when you constrain the machine to 10 gigabytes, the intent was we were trying to see what happens if I could do this on a desktop, for example. There are two ways of doing this. One is I could put this simply on an SSD and do effectively mmap those. And then whenever I need something through memory accesses, I can get the data through mmap. Other thing is to use traditional techniques for paging, and then say if you could use paging back and forth between those things. And you see what happens when you use mmap or for paging, the latencies blow up. And so they get to 183 milliseconds and 76 milliseconds and so on. And so our solution tries to keep the latency the same and while using the SSD, and that's the story I'm going to tell you, which is that I'm going to get to this similar to as cached latency nearly without having to have so much memory as 30 gigabytes of memory, okay? Okay, and how do we do this? The basic idea here is that, we'll just go back one more time. Okay, so when you get a query here that's shown in the dark, we're looking for clusters around the query which are close by. And then you're picking what are called potential candidates that are likely to be the answer to this query. And then you go through a process and then see maximum similarity and then return the documents that have the maximum similarity. So you're making basically picking up what are called candidate documents. So typically what happens is in order to get the results you want, you choose, let's say you're going to come up with 1,000 candidate documents, and you're going to go and evaluate those 1,000 candidate documents to see which one best represents the query. So that's basically what the pipeline was showing you earlier. So what we do is instead of visiting all of the clusters and then figuring out what to do with the documents, so what we do is break up visiting the clusters into two pieces. We visit the delta, whatever the delta number is, and then the remaining clusters, lambda, are visited in pipeline. And after we visit the delta clusters, we have a set of candidates from the delta clusters that we visited. I'm going to assume these are the best candidates, run with them in parallel in terms of fetching them through I/O, okay? And on the top, I'm still computing, going through the index and computing what is the likely candidates documents. So basically, I've broken up computing the document candidate selection into two pieces. 10% of the thing that gets done, immediately I take the 10%, assume they're the best candidates. I'm going to go issue the I/O for those. And the remaining 90% are getting done while my 10% of the candidates, I'm doing the I/O at this time, okay? And the idea is that now I can overlap the I/O for that 10% of the documents with the computation of the rest of the 90%. And if I'm lucky, at this point, this 10% is the best 10%, in which case I have the results by the time I computed them, and I can give you the results what you needed, okay? Okay, sometimes this may not work out, then I may have to go and fetch the documents that are missed, and that's the part I'm showing you here, calculate the missed documents and fetch those documents if needed, okay? Okay, all right, so each of this here is the contribution that my students made. Basically here, we were selecting the prefetching, this is basically we're prefetching the documents that we're going to prefetch. And then we're using the GPU Direct. This is a new feature so that we can move the data directly from SSD to GPU. And my student optimized some of the the kernel for CUDA to make things a bit faster. and then we compute the early re-ranking to reduce the ranking latency. Okay. Okay, we do all of this and hope that we can manage to do this. Okay, so just to give you an idea here, this data is showing you, so you can compute what is available based on the computation cost of the indexes and computation cost of the latency of fetching the documents, what is the size you have. But this thing is showing, these indexes use something called nprobe. Nprobe is the number of clusters you're going to query to see if they're close to the query that you're looking at. And basically, as you increase the number of probes, on the y-axis is the recall at 1K, which is basically telling you how likely you're going to get the document. It levels off after a while. Okay, so you can trade off this for a bit of a room to get what you need to do. Okay. Okay. This is showing you what happens if you change the prefetch step. What is the likelihood you're going to get the hit rate? How many documents are you actually going to need? What are you going to get in that prefetch? And you see here for most of these two data sets we've used to call MS Marco 1 and Marco 2, if you use about 10% of the documents to probe, you're getting about 80 to 90% of the hit rate, the accurate documents. Okay, so the prefetch hit rate is very high. With 10% of the things, you get most of them. And for the 20%, 10% I miss, I'm going to allow for that latency in the back that I showed you earlier. Okay? Okay. Okay, so here is the story, which is, if you see here, for the set 2, the bag of words index is 255 gigabytes. So there's no way you will be able to put this 255 gigabytes in memory. So we store all of this on the storage, and there is a CLS. This is the only index that we're going to leave it in memory. So we're reducing by a factor of about 1/9. This is the total index size is these two together. So we're basically keeping about 1/9 of it in memory. The rest of it stays in the SSD to move things around. Okay, so here are the results quickly. As you see here, this is for the set 1. We vary on the x-axis on the table 10 gigabytes, 15 gigabytes, 20 gigabytes, and so on, the amount of memory that's available. With 30 gigabytes, everything fits in memory. So nearly they're all about the same. But as you see here, as you reduce it here, ESPN maintains what is basically best possible thing at the bottom, even with different amounts of memory that's available. Okay? And the story becomes easy to see here. If I have this with the Marco version 2, this one says the 256 gigabytes is what you need to store everything in memory, more than 256 gigabytes. And as you reduce the amount of memory, the other approaches, basically the things quickly blow up. Okay? Whereas with ESPN, we nearly maintain the same amount of same latency across different memory configurations. Okay, so there's a whole bunch of other ablation studies to show. I'm going to skip this in light of keeping you guys here from going and getting some rest. So I'll just show you this, which is we have done a bunch of things here to get the performance. So if you take the data from virtual memory, the latency is 76 milliseconds. And instead of using virtual memory, you use GPU direct storage. And so that knocks it down from 76 to 58.3 milliseconds. So GDS is bringing that gain from 76 to 58. We use a custom CUDA kernel that reduces the latency by another 4 milliseconds. The prefetcher reduces it by another 6 milliseconds. Early re-ranking reduces it by 2 milliseconds. So this is giving you where the gains are coming from. And so this is basically go from 76 milliseconds to 46 milliseconds through various stages of things that we've used in here. Okay. Okay, so there's obviously some limitations here, what we have done. There's still a bunch of work to be done. First thing is we've used a single SSD here. Obviously, when the data is striped across multiple SSDs, we would have to worry about striping and making sure there's enough bandwidth. Other thing is as the size of the documents grow, the bag of word sizes can grow. we have to look at what happens as the document size grows. In fact, we would assume this approach should provide a better solution because as the data size grows, we should see more of an improvement. And we have done something for bandwidth, to make things bandwidth efficient. I didn't talk about it because of time, but there's still some work to be done to making this more bandwidth efficient. Here is the conclusion. Basically, we have found a way to optimize the pipeline for data retrieval so that bulk of the index could stay on the device and be efficiently retrieved by overlapping computation and the I/O retrieval by basically prefetching 10% of the documents. And those 10% of the documents that are prefetched seem to be most of the time the correct documents that we're prefetching 90% of the time. So we gain benefit by overlapping things. And we've reduced the storage cost, storage and memory requirements by about a factor of 8. Thank you.
Thank you. Questions? Yes?
Yeah, interesting work. I might have missed what you already covered. Is there any some accuracy evaluation? Because
Yes.
you talk a lot about this.
All of these are at the same level of accuracy. So in fact, these results here are produced at the same accuracy here. Okay, in fact, embedding latency. So so there are two parts to the paper. First part was not sacrificing any accuracy at all. Okay, so those results that I showed you, oops, I don't know what happened here. Where are the numbers? These numbers are all at the same accuracy. Okay, so we have tried to make this, we have looked at potentially sacrificing the accuracy here in order to make the things faster, and you see the loss in performance you could lose. So if you re-rank 256 documents, you're not going to lose any accuracy, but potentially what you could do is to reduce the number of rankings you want to try out, and if you reduce it to, let's say, 64, you are going to lose some accuracy. So that depends on how many documents you're able to retrieve. So if you only have bandwidth to get the 256 documents to re-rank, you're not going to lose anything. But if your bandwidth is only 64, then you would lose the accuracy by doing this.
All right, thank you.
Okay.
Any other questions? Okay, if not, then thank you once again. Hannes, do you want to say any final words for today?
Thank you for coming.
Thank you for coming.
See you at the reception.
Yep, so there's more to talk about, obviously. All right, thank you all.